Okay. Good morning, everyone. I'm Aditi. Welcome to PAKDD 2021. And I am one of the supporters. I would like to welcome Professor Naresh Manwani, one of the chairs, to host this session further.
Thanks, Aditi, for the introduction. So welcome once again for this first tutorial session in PAKDD 2021 version. So in the first tutorial, is the topic is very interesting. It is deep learning for code. And mainly the topics which will be discussed will be deep learning for programming, compilers, and code generation. And we have three very wonderful set of speakers today who have a wide variety of experience in industry and academia. So the first speaker is Sandhya Manarswamy. She's an independent NLP researcher. Before that, she had a lot of industry experience. The second speaker is Dibyendu Das. He's a senior principal engineer in Intel. And the third speaker is Dr. Ramakrishna Upadrasta. He's an assistant professor at IIT Hyderabad. So I welcome to all of you in the first session. And I would like to now hand over to the speakers. So Sandhya, over to you.
Thanks, Naresh. Let me just share my screen, just a quick second. I just wanted to confirm that, folks are able to see my screen. So just let me know, in case the screen contents are not visible. So good morning, everyone. Welcome to the tutorial on DL4Code, where we would like to talk about deep learning techniques for programming, compilers, and code generation. As Naresh mentioned just now, this tutorial will be presented by three of us. I would be I'm Sandhya Manarswamy, and the remaining two of my co-presenters are Dr. Dibyendu Das and Dr. Ramakrishna from IIT Hyderabad. Before we get started, just a quick intro about myself. Right now, I am currently working at Intel India as a principal engineer. I've been in the industry for around 20 years with different research groups and R&D organizations. And I hold a PhD in computer science from Indian Institute of Science, Bangalore. And my research interests are in natural language processing and applying NLP to different applications. And right now, looking at it, applying it to compiler optimizations and programming, and hence our interest in doing this DL4Code tutorial. And we would like to thank the PAKDD organizers for giving us this opportunity to present this tutorial at this venue. Without much ado, here is the agenda for today's tutorial. I would like to provide a brief background and context for this tutorial DL4Code. And then I would be handing over to my co-presenter, Dr. Ramakrishna, who would be talking about how we can model code for applying deep learning techniques. So when we talk about code, it can be source code, it can be intermediate language representation or intermediate code representation, or it can be low-level code, right, assembly code. So how do we create deep learning models so that we can apply DL techniques to code? And then Dr. Dibyendu Das would talk about applying deep learning techniques in the context of compiler, basically how DL techniques can be used in compiler optimizations, both in terms of replacing deterministic heuristics or rules, and also can be build automatic optimizations themselves using deep learning techniques. Then in the last session, I would be talking about a few applications for DL4Code, where we are using deep learning techniques to build software engineering tools and systems. For instance, how do we automatically do bug detection? How can we automatically fix bugs? How can we do deep code search and so on? And then we would talk briefly about what are the data sets that are available for DL4Code. Talk about what are the challenges in taking this topic forward, and also talk about some of the future research directions. So Let me just get started, and this is something which is very obvious to most of the audience in this tutorial. The progress in artificial intelligence and deep learning over the past few years has been humongous, right? We have heard of like driverless car and things like Siri and Cortana, and Google Assistants, where deep learning NLP techniques have been used in conversational systems. We've heard of even in the context of current COVID, there has been deep learning based systems which have been used for analyzing medical records, X-rays and CT scans to do automatic disease identification and so on, right? So the progress in deep learning and in specifically deep learning and NLP has been considerable, right? I mean, and there's no question about it. However, when you think about it, given that we have talked a lot about different real world applications, right? When we talk about NLP or natural language processing in the context of deep learning, most of the applications or systems have been built on human language text, right? I mean, when you talk about natural language understanding, where we are trying to infer meaning from text, the text is typically human language. It can be English, Hindi, Arabic, or Chinese, but the methods have been built to analyze text, which is used for communications between humans. Similarly, when we look at natural language generation, if you look at the current methods and models, many of them are again on the human language text, where we try to generate different text, English, Arabic, or Chinese, right? So the question before we talk about applying deep learning techniques to code is the following. Can we use deep learning methods on software codes or programs? Software code or program is not natural language, right? I mean, it's actually a programming language which humans use to communicate with machines, right? I mean, we give our high level intent in terms of a specific programming language, which is then converted or translated by the compiler to run on the target machine. So the first question we need to answer is, can we use deep learning methods on software code? Right. So, I mean, what exactly is the difference between natural language text and programming language text? Let's step back a bit and think about this. So when we talk about natural language text, how is it that we are able to apply deep learning techniques? Right. One of the main fundamental principle on which statistical NLP techniques have been built is the distributional semantics, right? I mean, this is very famously known as the Fritz law. Your word is known by the company it keeps. I mean, or in other words, if it is a context or the surrounding words that gives meaning to a specific word, right? So even if there are words or phrases whose meaning the system cannot figure out directly, it can infer it from the context. And the statistical NLP techniques are built on these cornerstones. And this is because natural language or human language text is typically repetitive and highly amenable to statistical analysis. So the question that first we think about it is does this property hold for programming languages also? So, but if you look at it in theory, programming languages are very complex, right? They have considerable capabilities. You can use them in many different ways. And it's highly flexible, but at the same time, quite complex. Right. So the question that stares at us is are they amenable to statistical NLP techniques? But when you actually look at the natural programs, by that, the actual programs that people or the human beings write, they're found to be empirically simple and rather repetitive. I mean, this is something all of us can very easily relate. I mean, if you're writing a C code, most of us would say for I equal to something, low range to high range, right? I mean, it's a natural intuitive thing where we sort of repeat the kind of code constructs. So programs also have useful statistical properties which can be predicted. This leads us to the fact that, you can model programming languages or source code or intermediate code representation using statistical language models similar to the human language text, language models for human language text. And using that, we can actually leverage it for software engineering tools or compilers and so on. The whole notion of programming languages being amenable to statistical techniques again is because of the fact that there is considerable repetition, right? So repetition can occur at many levels. At the example I gave about for I equal to, where I gets used as an induction variable in a loop, right? I mean, that is something which happens at a lexical level. You can have code idioms which are having syntactic repetitiveness, where two code fragments get repetitive because we use a similar syntax. Or it can be semantic level, where there is no surface repetitiveness, but the underlying functionality is same, right? So this characteristic that there is repetitiveness or regularity in programming languages or programs which human beings write lends itself to the fact that we can apply NLP techniques, natural language processing techniques, on programming languages and source code also, right? But the other question now comes. We all know that deep learning models and deep learning methods require large amount of data, right? So given that fact, do we have large amount of code databases which can be used to build deep learning techniques or models for analyzing source code and intermediate code, right? Over the past few years, we have seen the emergence of large amount of open source or publicly available code repository. All of us are familiar with GitHub, SourceForge, or Bitbucket, right? We are this large amounts of publicly available code, and it's possible to use this big code. I mean, the so-called big code similar to the big data, which can be used to build deep learning based models for programming language code or intermediate code. So that sort of brings us to the topic of our tutorial. The fact that big code exists, the fact that programming language, source code, and intermediate code also exhibit naturalness allows us to come forth with the DL4Code, where we can examine applying deep learning techniques to code also, right? So the whole intent of DL4Code as a from the software engineering perspective is that there is considerable inherent knowledge which developers are embedding into code. So when we are writing different software, different programming projects, or different code systems, we are actually building in a lot of knowledge into the code. And this knowledge can be mined by means of deep learning techniques and reused to create smart software engineering tools, whether it is programming assisting tools like code search or clone detection or code summarization, or by tools such as compilers, where we can use it to build better optimizations or improve generating very efficient code. These are kind of the topics we are going to talk about in today's tutorial. Before we talk about how we apply DL4Code, we need to understand how can we model code itself using deep learning methods. Dr. Ramakrishna would be starting off with that. And as I said, we would then follow it up with applying deep learning methods into compilers and other applications. So over to you, Dr. Ramakrishna.
Thank you, Sandhya, very much for the nice introduction, as well as to Dr. Naresh for arranging this. It's a real pleasure being this tutorial. So just a small some caveat. I am a compiler's person, and I somehow came into this area. So just like Dr. Sandhya mentioned, talk about modern program documentations. This is work done with my students. S. Venkatagiri is my PhD student, along with other students, Rohit Agarwal, Shalin, and my colleague at IITH, Dr. Monendra Shankar Sarkar.
Ramakrishna, can you speak up a bit? It is breaking a bit. Yeah, can you just speak up?
Okay, okay. So, yeah. And as well as Professor Bayan Srikanth from ISC. So, so I think the brief outline for this talk. So we are primarily going to talk about the necessity of program encodings. This kind of intersects with what Dr. Sanjay mentioned. And then we are going into characteristics of a good program encoding. What is a program encoding, and how do we classify or characterize a program encoding as good or not good enough, etc. And then we understand the various facets of encoding. We have a threefold classification of the encodings. And then we see case studies, multiple case studies. There are a couple of papers from Israel. There is one paper from ETL Zurich, and then there is one work from our group itself. We'll cover them, and then finally we'll summarize. This is the outline of this talk. So anyway, you all know that what you all, there is program representations. There is a lot. You are really living in a lot of code. There's GitHub, there's Bitbucket, there's SourceForge, Stack Overflow, Code Snippets, Stack Exchange, HackerRank, etc., etc. All this really leads to big code. There's code everywhere. Many of them are correct codes. Many of them are incorrect codes, etc. You will find the students, for example, in classrooms, they submit some sorting programs. Very likely, they all make the same mistake because the original location where they copied from, it had the same mistake. So I think, but anyway, we are really living in the world of big code, and this big code poses a lot of challenges. We are in an important problem. So whether it is in the or whether you want to build automated tools. For example, you have the user, he or she is typing the code, and then you want the code suggestions in a nice manner, or you want to show some errors, etc. Some similar code. Yeah, hey, you have typed in something like this earlier, etc. Or you want to improve the performance of the code. Performance is in a very standard compiler theoretic way. Whether you want to improve the time, energy, memory, etc., etc. So, and when you go to so these applications, I call it as software engineering applications. And you may want to do similarity detection. For example, you are given a whole bunch of codes or code snippets. We'll see why this characterization, why this specialty is important, and then we'll understand. And then you want a quick summary of the code. You have a lot of code, and then you want quick succinct summary, and then maybe you want to use this summarization for commenting, etc. And then you want to do automatic code suggestion. You can build it into some GUI so that it will be useful for the students, etc. For anyone, for any programmer. But actually, this boils down into some undecidable problem. Rice theorem, etc., all the way back, nearly century back. So undecidability really bites us very heavily here. And when you want to do compile automations, you want to have the standard performance improvement. Whether you want to inline the code, whether you want to unroll the loops so that inline the functions, unroll the loops, etc., or you want to vectorize, for example, or you may also want to do phase ordering. Phase ordering is a very compiler theoretic problem, but it is very important. Phase ordering can improve performance by good amount. So it turns out that these problems are anyway NP hard and NP complete, as most interesting compiler optimized problems are. This also is NP hard and NP complete. So how do we handle this? I think now in the current world, how to solve these problems? So obviously you can guess that we use this thing everywhere. We use machine learning, just like everywhere else. Machine learning, with the pervasiveness of the machine learning, it's a good opportunity to use machine learning here as well. So that's the overall thing. So as we want to get to that, for getting to that, we want to understand how can we represent a program. Analogously, when you're going to NLP, you have these representations, word to word, glow, etc., etc. And images, you have these various networks, CNN, AlexNet, etc. So the natural question is that for programs, what are the representations and how do you classify them, characterize them, etc., etc. We can actually give some characteristics that a program embedding should satisfy. Ideally, we want it to be independent of both the source language as well as the target architecture. For example, you just like compilers, you really don't want it to be very specific to one language, and then you really don't want it to be particular to one architecture. So there should be some independence to both of these. and we want that embedding to capture both the syntax as well as semantics, like our Dr. Sandhya explained right now. So syntax is sometimes important. For example, plagiarism detection, you may want more syntax kind of application, and semantics you may want to do more similar codes. You want to classify the codes, etc., etc. And then you want to use these embeddings for various. I use these embeddings or encodings in an interchangeable manner. But you can read our paper. There is subtle difference. But in this talk, I'll cover embeddings and encodings in a very interchangeable manner. So we have diverse. You can apply them to diverse applications. And like we said, we can use it for either software engineering applications or even for compiler automation applications. For example, let us you want to build tools using this, or you want to improve the performance of codes. So program embedding should also be scalable. Obviously, you should have faster training time. You should use less number of GPUs. You should use lightweight ML models. For example, you are using a GUI for typing code, and you want program solutions. The model should not be so heavy that that itself takes a lot of CPU power or memory, etc., etc. You want it to be a lightweight model. And in general, you should have no out of vocabulary. We'll keep referring to out of vocabulary. Out of vocabulary, I'm sure you know it better from your natural NLP and other areas. But you have seen some amount of inputs. Can you predict something on? Can you add something on something new, or are you just predicting something based on what you have already seen? This is you really want to go beyond what you have already seen. That's kind of my definition of out of vocabulary. So you want the program representations to satisfy these characteristics. So we can broadly classify the encodings in a trifold manner. Whether they based on the representations, how you are taking the program and representing it, or embedding techniques, how you are actually constructing a vector out of it, what methodology you are using to construct a vector out of it, or what applications you are using it to. Okay, so these are the three facets, what we call encodings. So let's go through these 3 points one by one. The representations is a very standard compiler based what we call characterization. I'm a compiler person, but I think here what happens is that you can either use lexical tokens. You may have taken a basic compiler course, and compiler what we call lexical tokens. They have been used and pretty successfully as well. For example, there's a very famous paper called DeepTune. It uses very lexical tokens and some more information, and you use these lexical tokens, and then the tokens themselves can be mapped to some kind of word-to-vec kind of model. You send the tokens, and then you can use NLP techniques. You are kind of, I mean, just like Dr. Sandhya mentioned, you are kind of taking programs and then using the what we call NLP theory, which has been developed over the past 30-40 years, whatever. And then using programs as some extensions of NLP, natural languages. But you can go beyond that. You can go more deeper into compilers, because programs are quite interesting in their own world, in their own way. You can use abstract syntax trees. Abstract syntax trees are very standard representation of programs. They are output by the parser of the language, and you can also go deeper. So you can have intermediate representations and program dependence graphs. So primarily this talk will talk about lexical token based encodings, AST based. I use AST for abstract syntax trees and intermediate representations. And there's a joke here, intermediate representation. I mean, when you go to this machine learning or natural language NLP communities, IR mostly means what to call. It doesn't mean intermediate representation. It means information retrieval. So please bear me when I say IR. I mean to say that intermediate representation, not information retrieval. Okay, and then you can use program dependence graph. You can use control dependence graph, more powerful techniques. So let me go to something. Yeah. So Professor Iran Yahav from Technion, he has a very beautiful slide. He classifies the these various representations as using lexical tokens, AST, intermediate representation, program analysis info. Lexical tokens are very easy to obtain, and then AST is you have to consider the parser and you have to clean up the parse tree, etc. And then you have to go through these intermediate representation that takes a quote unquote conversion by itself, and then you can construct program analysis info from this. So as you can see that at this end we have syntactic richness, and this end we have semantic richness. So as you can see that this, as you go to the right, there is more program analysis effort and complexity are required. And as you can imagine, the ones on the left, the lexical tokens, etc., they need more learning effort. For example, learning effort could mean more training time, more training data, etc., etc. And while these are costlier to construct Excel in another manner. So I think there is a trade-off here. Just like many problems in compilers, there's a trade-off here. There's what you call, every problem has its own sweetness and its own application, etc. So you can also, just to use some compiler terminology, these lexical tokens and AST are mostly, you can classify them as front-end based representations. And there's something called, I mean, mid-end is a very strange name. Many people don't like it, but in compilers, but I think let's call it intermediate representations as mid-end based representations. And then you can have more program analysis, more back-end representations, etc., etc. Please hold on to this slide. We'll come back to this probably at the end of this talk, and then we classify the various techniques which we have studied in this block. So just to tell, so that this IR is intermediate representation. So there are many intermediate representations proposed by compiler researchers, but one which has been successful is both a compiler as well as an intermediate representation. So it has broadly, it has front ends, so it has various languages, C, C++, Fortran, etc. And then that is converted into LLVM IR, and that takes, and whole LLVM, what we call, it follows this block by block framework, and then we have that spits out the optimized IR, and then backends for various architecture. This is the overall schematic of entire LLVM. And if you if you see a standard program, sum int a b, it takes 2 integers and then it returns the sum, and then a main to handle this. The intermediate representation is, you can think of it as something like an assembly, but not really architecture specific. So in a very loose manner, you can think of it as a architecture independent assembly. Maybe Professor Divyendu will excuse me for using this, but what call you? So you can have define I32. It takes an int, and then you have some, and then int a, int b, etc. And then you have some what we call memory management instructions, etc. Then you have a variable that takes these. Then you have variables which load a and b, and then you have an addition here. You can see the addition here, and then you add 3 and 4. 3 and 4 correspond to this a and b some way. And then you return the value that's computed as %5. This is how intermediate representation looks like. So I think this is the starting point for our encoding, but and encoding from ETH Zurich as well. So by the way, the backend looks like this. We don't need it for this talk, but and why LLVM? LLVM because it has been used on 2 successful embeddings, program embeddings. LLVM is a very standard infrastructure, etc. And LLVM supports many languages. For example, C, C++, Fortran, and a couple of other languages as well. These have been very widely used. So we want to build from a program documentation that is language and architecture independent by itself. And then we want to build an encoding from it. We want to build what called quote unquote code vector for it. Code vector means a what called continuous vector in some high dimensional space that that corresponds to this particular program or entities in the program. That is what we wanted to do. So for this, ideally, like we discussed in an earlier slide, it should be both architecture independent and language independent as well, ideally. Okay. So I think. The second point is that the second facet of encoding is the embedding techniques and learning representations. The what we call embedding techniques also, they can be based on what we call as a very straightforward NLP based token embeddings, or they can use non-sequential models, or they can use sequential models or GNNs, graph neural networks, or even attention models. I mean, there are use cases in our talk itself when we talk about this. For example, Chris Cummins' Deep Tune, it uses what we call token-based embeddings. It uses little more, but it can broadly be said to be token-based embeddings. And then we have non-sequential models. Non-sequential models is, for example, our framework that's called IR2VEC. It's a non-sequential model. It uses just a ML-based model, etc. And then you have sequential models. For example, the very famous embedding technique from Technion Israel, that's called Code2VEC. It's a sequential model. And then you have later works, Program ML from Chris Cummins and others, and attention models, another work from Technion. These are that use attention. So you can actually have various facets of encoding, and each of these can have their own power, etc. So coming back to this is a very half a minute slide. I'm not a master in representation learning, so but I'm sure you know this. But representation learning is just a branch of machine learning. It where you can learn the representations by automatically extracting the useful features. For example, you give it a dictionary, and then what call you send in all these kinds of all words. They are clustered together. You run a clustering algorithm. For example, man and woman are clustered together. Apple and orange are clustered together. Dog, fish, cat, etc. They are clustered together. And then once the clusters are formed, you can ask various analogy questions. Analogies, for example, man is to king, woman is to what, woman is to queen. So answer is queen. So I think these can be inferred from the clusters. So this is a branch of ML. This is very much widely used, very successfully used. For example, whenever you're typing any Google search, internally things like this are very cool things are happening. So we are going. We'll come back to these analogies later in this talk, because one important facet is that you wanted to have programs. This program is to this program, then this program is to what? Okay, that's kind of nice. You really wanted to get to that stage. So that's why this is relevant. And the third facet of encoding is the applications. It's the moment you get a proper encoding, and then it characterizes it satisfies certain characters, what calls it has certain features, then it can be used for various applications. So firstly, we really want to understand whether our encoding is application dependent or application independent. This is very important, because application independency may seem like cool thing, but sometimes maybe you just want to write a simple plagiarism checker, etc., or some specific task. For this, application dependence may actually be what you call be more important, more successful, because the accuracy rate is very important for ML. So application dependency versus independent method, this is a very important characterization. And then they can use the software engineering, like we saw in a website, code summarization, method name prediction, etc. Some Code2VEC it uses method name prediction, and then program recognition, for example. And then this is used for, has big implications in security as well. For example, right now we are in quite insecure world of all these malware, etc., etc. And even our security lab, our DRDO, etc. You want to automatically detect these what you call malicious programs, and you want to use neural networks for that. As part of that, program documentation is very important, and it also can be classified to be a software engineering what you call application. And then we have standard, very important high performance computing or compile optimizations. We have GPUs, we have CPUs everywhere. You want to get good performance on them. You want to take a piece of code and automatically tell whether it runs best on CPUs or GPUs. That's very important. You want to characterize its memory caches, etc., by using neural networks. You want to do thread coercing. These applications are covered by the later talk by Professor Divyandu. And then you want to do various vectorization, digital location, inlining, etc., etc. And then you want to use for various code generation techniques. So this brings us to the next section of our talk. Next section of the talk is about representation models. So I think before we go into this, we are going to cover 4 or 5 papers. You can see a gradation in these papers. You can see the gradation in the papers, both in the input as well as in the methodology they are using. Input, for example, some of the earlier techniques which I are going to study, they use, for example, just a very straightforward application from NLP techniques, and then they use they just use lexical tokens. And then later we'll see techniques which use AST representations. Later we'll see ones which use intermediate representation. And the methodology as well. Some of the earlier techniques, they use NLP techniques. They use what I call word-to-vec kind of application to programs. The other later techniques, they use attention layers, they use LSTMs, etc., etc. And then finally, we'll see techniques which which use lighter models. They will use more program analysis, etc., etc. So there's a whole gradation here. So let's be this is just around 4 or 5 papers. Then we'll go to IR to it. So representation models, one of the first techniques was worked by Iyer and others. It was published in SCL 2016. It's called CodeNN. It's a it's a primarily token-based representation, and they take code snippets. Code snippets means please mark it, because if you wanted to represent a code, do you want the code to be compilable unit? That's very important. For example, you see code snippet in Stack Overflow. That's mostly not a compilable code. It's just a small chunk of 3-4 lines of code, and you wanted to characterize it. You want to automatically read it, and then you want to build a machine learning model by which they can be given tags. That's very important. So these authors, what they do is they they use these code snippets to give comment like summary, to automatically generate comment like summary. The architecture is an LSTM based one. So for example, they take these what called code tokens, C1, C2, CK, etc., and then they generate a what is called a one hot vector. It's a matrix where each columns are the vector representations of the tokens, and then they send it through an LSTM. They send it through an LSTM, and then there is an attention layer everywhere. Attention layer. For example, the code tokens, they are sent in through the attention layer to get the first token, and then this particular word token, which it gets as output, it is again sent to get the N2, etc., all the way till the end. So as you can see, this is the steps of the LSTM, and it spits out N1 and 2 all the way till the end. These N1 and 2, they can be considered to be the comment like summary of this particular code. And it uses attention layers. As you can see, attention layers are used, and as you can see that it combines both the code tokens as well as the text tokens. So this kind of the it has been pretty successful paper, and the same they have used it for comment like summary for code snippets, and then they also apply it to C# and SQL. And this particular data set has been used by a later paper from Technion, Israel. So this is and then this leads to a pretty important paper called Code2Vec from Aaron Yahav's group. It was published in POPL 2019. They had a whole series of papers. In the same year, I think they had a POPL paper as well as ICLR paper. So it's a the input to the they solve the same problem. Use the AST representation for for code summarization and method name prediction. So what happens is that they use the AST representation as input, and then they, as you can see, the ASTs of the individual, let's just call it context. They call it context. Context is some kind, some path in the AST. That's what we'll call. We'll get to it in a minute, please. This particular context which they use is very similar to the word-to-vec context. If you already know word-to-vec, it's like whatever applying that to this area. Okay, and then these context vectors, they go through a fully connected layer, very standard fully connected layer, no complications here at all. And then once these individual context vectors, they go through this fully connected layer, we get a code vector. And when it is combined with attention weights are again, as you can imagine, they are pre-trained, etc. And then they go through the code vector, and then they go through the softmax, and then which can be used to predict for prediction of method name, etc. So as you can see, there is a fully connected layer is used. It's a non-sequential model, obviously. And then attention weights are used, and then there is certain importance to path, and they have been applied to. By the way, this encoding, it's a application dependent encoding, and the vectors, they don't seem to generalize. Generalize means they are using for method names, but can they be used for comment generation? Can they be used for some other applications? They are at least not exposed outside, so that if one wants to apply it to other application, etc. But the results are very nice. It has been accepted in Popple, and for example, they have shown the use case in Java programs. But they also claim that this is very easy to extend from Java to other languages, etc. You just have to build new parsers. It will take care of it. So this is so now we are left with understanding what this context vector is and how ASTs are used. Very standard compiler thing. You have a source code in fun in T, and then in T is equal to 90, return T plus A. I mean, bear me for 10 seconds while I go through what a AST is. AST is like a tree which is pruned parsley, etc. You can have in fun parameter has what we call two children in T, and then you have a block statement. Expression block statement. This entire thing leads to a block statement, and then you have an expression statement. Is the first child, and the return statement is the second child. Here you are, first child is this, and second child is this, and the second statement leads to a variable declaration expression, as well as whose children are int and variable declaration, for which A and 90 are the two children. That's standard, and then the right hand side return binary plus, as well as T and A, T plus A. Okay, that's a standard thing. So what they do is they call the paths in the AST from one child to another child all the way through the AST. You can enumerate these paths, and then you can actually send it to the you can call it a context. You can call it a context, and you can send it to the neural network. So you can see left leaf context, as well as the path, as well as the right child. They form these three. That's the magic. That's the secret behind these three dots. You can have fun all the way till in the path, as well as the right child is the 90. So this constitutes a path, and then they enumerate this path, and then they send it. That constitutes the context. Okay, and then this has once you construct this context and training is done. Then it can be applied for various things. For example, you see this particular code in F, taking just a string, as well as it's doing some fancy stuff, and it turns out that it looks like it is counting something in the program, and so they claim that so it gives a probability or conditions, etc. Called confidence. And for example, this particular code is 42% looks like count, and 33% it looks like count occurrences of, etc., etc. So it has been successful, and that's it. So this sets us to the second paper by the same group. I have this group. There's the same student, Alan. It was the ICLR 2019 paper. They called it code to seek. I mean, as you can get from the name itself, it's like built from word to seek. It's a sequential to sequential model. And then this particular section, this initial section, is very similar to the code to X initial section. You have this left child, and then you have this path, and then you have this right child. They are all sent to a fully connected layer, just like code to vector, code to vector. That's very standard. The unique part about it is the decoder aspect. Decoder aspect is, as you can see, what you call, you can see sequentiality here, so you can guess that it is either LSTM or RNN. And what happens is that attention is used, and attention it gives it somehow automatically it gives more importance to pass, and it has been used again for method names, but it gives the output token by token. And it has also been used for C# for code captioning. This is the same data set that was proposed by Iyer et al. Because it's important, because Dr. Sandhya earlier was mentioning that data set, how do we talk about data sets, what happens, how do we create large enough data sets? That's an important, how do we create labeled data, as you well know, is important in image processing. In a similar manner, how do you create labeled programs in this, Anyway, that's fine. So they have, so this, for example, for this particular code, the decoder, it brings out the token by token, and for example, it brings contains, ignore, case, etc., etc. If we focus on this particular example, you can see, I mean, some of this is kind of magic, but I think some of this can be explained nicely. You can have set and set. So set mostly has implications with contains. So you can have brown guy, which is brown path. It talks about contains, and then we have a blue path. Blue path has from entry to equals ignore case. So I think it's printing out. It focuses on ignore word. And then this green path, it is from set to equals ignore case, and it is printing the case. So I think what we call code summarization, it is some summary of the initial section, some summary of the level by level thing. So that's and it had the results have been very successful by code to seek as well. Okay, that closes off the AST based encodings. And this was in ICLR 2019, and that brings to the next work, which is from NURIPS 2019, that is from ETH Zurich, and Torsenhofer and others. So as you can imagine, they are also built from LLVM-IR, and LLVM-IR, we have seen it. It has various front ends, etc., and it is also based on SSI representation. And then they construct something called a context flow graph, XFG, and that leads to an encoding called inst2vec. So when in parlance, in other papers, inst2vec and NCC, they are kind of used interchangeably, and then they send it to an RNN, sequential model RNN, and then they claim that it can be used for various applications. So input is again, I mean, as you can see, it's an LLVM-IR instructions. The architecture is RNN. In particularly, they use the skipgram model, and they use an unsupervised learning, and they use an beautifully, very nicely. It's an application independent encoding. While you see that code to seek and code to vec, for example, they are application dependent encodings. Let's get back to our NCC. NCC application independent encoding, and you have a program classification. They have been applied to primarily program classification, as well as two important HPC applications originally defined by Chris Cummins of Deep2 when he's proposing this Deep2 paper, and the device mapping and thread coercion. We won't go into the details, but about the encoding itself, you can see that the standard C program, it's converted into this LLVM program, LLVM-IR representation, and we may not have time to cover all this, but maybe at least what I can do is, so you can think of this as a data flow basic block. These, for example, this particular instruction leads to this particular graph, mini graph, let's call it. So you can have a percentage comparison, and then percentage x 5, percentage x 5. That leads to these small graphs with no control flow edges on it, And these particular there is an analogy here. These particular small treelets, let's call it, treelets could be considered to be similar to our TensorFlow operators. So, but there is still no control flow. So these particular small trees, they can be connected using control flow edges. For example, the blue edges, I think, are the control flow edges, and this overall thing leads to a contextual flow graph. And this contextual flow graph can be sent to an LSTM sequential model, the LSTM, and then you can directly apply word-to-word techniques, etc. It's important to know that this is a IR-based encoding, but in some sense it's unique. It's very good. It was the first one to use IR-based encoding, but it is not really using any program analysis information here. So that's important to know. And then we get to this work called IR2Vec by our own group. It's by my student Venkatiti and others, etc. So broadly, IR2Vec was inspired a lot by MCC and other works, but we use this program analysis information in some manner. So broadly, IR2Vec has one is called the training phase, as well as followed by inference phase, followed by downstream task. So input is anyway LLVM IR entities. For the architecture, we use translation model. In particular, we use TANC, and then we use unsupervised learning, and the encoding is program analysis based. And then our encoding is application independent. What we call, and we have used for program classification and device mapping and thread coercion. The published paper, it has only device mapping, thread coercion, but we have other results in both in HPC, as well as we have more results as well, upcoming results as well. So what is IR2Vec? What is IR2Vec means? You first have to understand what a basic block is. Basic block is something like a single entry, single exit region in a program. So you can have some kind of memory allocation, some kind of load and store, what we call instructions, followed by an addition. So you can think of this particular instruction: store I32 %A I32 pointer a dot address, and then line4, some kind of instruction in what we call in LLVM. This leads to good bunch of tuples. You can consider them. For example, you can have store. Store is a type of, and what we call it's like a tag. Then integer ty because store, this is the integer type store. And then you can have a next instruction. That's a standard next instruction that happens. Just like you can think of it as a bookkeeping instruction. And then you can have arg1, arg2 for this instruction. Arg1 is a pointer, what we call variable. Percentage A is a normal variable. Argument 2 for this instruction is a pointer variable. You can see the star here. So this leads to these bunch of tuples. And for example, analogously, for the return instruction, you can have return type of integer ty, and then you can have next argument is arg1 and variable name. Okay, so you can see that the variable names, whether they are percentage A, percentage add, they are kind of stripped off because we really want to lose the what we call we want to lose the lexical information. Okay, and then these tuples, as you can imagine, they are sent to the TANC model. They give HRT, head relation tail. They give these relations. They are sent to this TANC model, and then and the TANC model it learns H plus R is equal to T. Okay. Am I audible? I do this in the class.
Yeah, Ramakrishna, but slightly higher would be better, but it's okay.
Oh, acha. Okay, I'll do that. Okay, thank you. So I'll do that. Thank you. So H plus R is equal to T is what is learned by the model, and on training, what happens is that the seed embedding vocabulary is constructed or built, in which you have clusters of various. This speed embedding vocabulary is pretty important to our LLVM, what we call for our IR to but it's surprisingly it has very close. It's very small, just 64 entities, and so this is, we can call it as phase 1 of the training. Once you have this seed embedding vocabulary, each of these instructions, they can actually be what we call, you can construct the encodings for that, embeddings for that. If, for example, you can construct the embeddings for the store instruction, as well as for the type, as well as for each of these arguments. Using this, you can have a linear combination of them, and then that will lead to the embedding for this particular instruction. And in a similar manner, for return I32% add, you can have the embedding for W0 as well as WT, and then WA. These are the what we call some magic weights for the operator, for the type, as well as for the arguments. These are tunable parameters, but what we have experimented with a couple of choices for this. They are what we call hyperparameters. But we have converged on some linear combination of W0, WT, WA will give the weight vector for the encoding for this particular instruction. Okay, so we are done with the constructing the seed embedding generation. Then what do we do? Then how do we proceed? We can have a source program, whether it could be in C, C++ or Fortran, and then we can have LLVM generated from it. It's a very standard pass, quote unquote pass in LLVM, and that leads to instruction vector for each of these individual instructions. And then this is what we call as symbolic encoding. Symbolic encoding is just the instruction vectors, individual instruction vectors, etc. Then they can also be embellished, or embellished is the right word, embellished with use def and reaching definition, some classic data for analysis. This classic means 1970s or 80s data for analysis. You can use data flow. Data for analysis is broadly which data, which what we call definition is available where, etc., and where whether a particular variable is live in a particular location or not, a particular program point or not. So once you kind of embellish, we'll get into how do we do this. What we call make it more rich using data information little later. The next slide, I think. That leads to basic block vector. The instructions in a basic block, they can be combined in a nice manner to have the vector for the basic block, and a bunch of basic blocks in a function. They'll combine in a nice manner to lead to the vector for the particular function. And as you can imagine, next step is you can have a program has a bunch of functions, and the encodings for each of these functions, when they are combined in a nice manner, you get a program vector. So this is the vector generation. The beauty here is that they say we follow a modular a generation of these encodings. We can have basic block vectors, which are these have very close correspondence with how LLVM itself is designed. You can have basic block vectors, function vectors, and program vectors. And once these embeddings are there, you can use for any downstream task. We have used for some applications, but more are possible and currently upcoming as well. So that was what we called as symbolic encodings. And this leads to something called flow-aware encodings. Flow-aware encodings, and there are two sections to flow-aware encodings. Whether they are intra-block, means intra-basic block what we call flow, or inter-basic block flow. As you can see that a good bunch of instructions, single entry, single exit, what we call bunch of instructions are called basic block. They constitute a basic block. You can have a variable which is assigned here, and some other instructions, etc., etc. So very straightforwardly, what you can do is you can construct the embeddings for this instruction, etc. If you do that, you are in a comparable method like what we call NCC encoding. Not really the same, but in a similar manner. But here, what we do is we more use the what we call we embellish with the data flow. For example, this encoding for I1, the square bracket I1 is the embedding for I1, and the square bracket I2 is the embedding for I2, etc., etc. This particular variable percentage address array address, it is used here. It is used here, and then that's it. Let us assume that it is not used further down this basic block or further down the program. The only usage of this particular variable is here. So in a compiler terminology, using compilers, etc., what happens is that this particular definition is said to be killed here. Okay, it is not needed further down the thing. Further down, in a similar manner, you can also use the particular vector. Once you construct the vector here, you can immediately use it here. You can use the intra basic block data flow. You can use this particular what I call embedding encoding here while you are constructing the embedding for I4. In a similar manner, I2 can be used for I5, I3 can be used for I3, etc., etc. I3 can be used for I6, etc. And then you also have to go through this kill and update of I1, I2, and I3. This is how we have applied the standard terminology from compilers while we are constructing the vectors inside the basic block. But that's not all of it. You can have inter-basic block as well. You can have a standard program. There's probably an equivalence here, and then there's probably a loop here, etc. You can have basic blocks. You can have programs like this. For this particular instruction, you can construct this I2 is W0 of alloc plus WT of integer type. Okay, that's easy. And then you can have this particular I4. I4's encoding is W0 load plus WT of pointer type. So there is a pointer here, there is a pointer here, and now comes the fun part. The fun part is that this is the arguments for this are I2 plus I3 plus I9. You can see that I2 is used here. That's very natural. You can have I3 which is used here. That's also very natural. But I9 it's like a little mysterious. Why is I9 being used here? Because that comes from aliases. It turns out that this is a pointer, and I think Y and J are aliases to each other. The pointer determines that. The pointer analysis determines that, and that can be used for constructing the encoding for this. And similarly for I5 as well. So this is what we call as flow-aware encoding. Broadly, our paper talks about symbolic encodings, naturally construct the encodings without resorting to data kernels, etc. And then we use this flow-aware and we propose this flow-aware encodings, and then flow-aware encodings uses data flow information. And this has more advantages. It has for program classification, for device mapping, etc. Then these are better for flow-aware encoding. Okay, so it has to be mentioned here right now that when we are you have individual instructions, and how do you compose these vectors? That itself is an important choice. For example, you can actually you have individual instructions. They get you these vectors, but you can actually combine them using linear combination. That's easy. That's straightforward. But you can do more. You can actually construct a sequential model, and then combine the vectors, or you can use non-sequential model. This is important and pertinent to mention because the IRTOVIC published paper that uses this, but there are other applications where you can use sequential models. That's what we are currently using, and non-sequential models as well. So and how vectors are composed, how the data kernels come into picture. You can have this is a little compiler theoretic paper slide, but please bear with me. You have live variables and field variables. They are very standard terminologies in compiler analysis, program analysis. You can have live variables. It is instructions, the ones which are generated minus the ones which are key, etc. And then the basic block is what you call, you take the instructions that are live. You take the vector for that will give you the what you call vector for that particular basic block. In a similar manner, a function has a bunch of basic blocks. So a combination of these basic block vectors will give you the vector for the function. And for a program with n functions, f1, f2, fn, you can combine these functions in a nice manner to get the encoding for the particular program. So I think this combination, we are currently talking about just the linear combination currently, but we can actually use LSTM, we can use more fancy stuff. So we have, pardon?
I think Sandhya has some question.
Okay. Please go ahead.
Yeah, you have raised a hand.
I'm sorry, like, I mean, I think that is by mistake. Like, I mean, I'll just do an unraised, like, my apologies.
Definitely, no problem. That's it. So I think no problem. So, so we get these code vectors, and these code vectors, they lead to some kind of just taking these code vectors and then training them. It leads to some nice clustering. For example, you can cluster the LLVM instructions in a nice manner. It turns out that because of this encoding, you can have the arguments, for example, function pointer, variable, constant, they are clustered together. The integer operators like reminder, division, multiplication, etc., they are clustered together. And then the floating point operators, they are clustered together. So, kind of cool to know. In a similar manner, we can have the pointer ops. Pointer ops are the alloca, etc. They are clustered together, and the integer ops, they are clustered together, and then the floating point ops, they are again clustered together. And similarly, you can have cast operators. You can have, for example, you can cast from integers to floats or floats to integers, etc. Cast operators, they are you have integer operators here in blue. You can have the floating point operators in green, and cast operators, they are kind of in between, you know, kind of cool to know. And then you can have types, they are in their own world. So this clustering automatically happens. So it looks like something is happening. Okay, now comes one interesting mini application. Let's not call it major application, but mini application. Instruction analysis. Instruction analysis is something which we have seen. You have seen this king versus man, etc., man versus woman, etc., that kind of thing. King versus queen, man versus woman, etc. You can have sign. You can have. Let's take a simple example. FDiv, floating point div, is to normal division. Then multiplication is to what? If you ask it, somehow it is learning that multiplication, integer multiplication comes here. So, but this is syntactic. It is syntactic, and for example, you can have call is to return. In a program, call is to return, then switch is to what? Then switch is to label. You know, switch has a label here. You can typically ask queries like A is to B, then C is to what? Then on it is constructed like B minus A. You can add it to C, the vectors, and then that will lead to this. So we are currently using this closest neighbor for this. These are nice. These are nice and easy. Load is to pointer, store is to constant variable, etc. But these are syntactic. But these analogies, they go beyond that. It's very nice to know that integer division is to shift right. Then multiplication is to what? It is learning that it is shift left. You know, that's kind of beautiful in its own sense. For example, you can have shift left is to shift right. Then OR is to what? OR is to AND. And it is learning these semantic ones as well. Division is to reminder, and UDiv is to U reminder, etc. So it is learning these analogies in a nice manner. So machine learning actually is up to something in a proper manner. So that's kind of nice. So we use it on similar setting like our NCC, Instuvec or NCC. we applied it for various applications, CPU versus GPU device I'm already out of time. Detecting optimal device mapping. There our professor Dividras will cover this application in detail, and we also applied it for predicting optimal threat cohesion factor and program classification. So yeah, we won't talk about results right now. I request Professor DD to take over when we do it. There are some other models. There are some other papers which have been proposed in the past couple of years. This is a very emerging area. There is a flow to it last year, Oops law, and then there is a Wang et al. Again Oops law. I think they both received some best distinguished paper kind of award. And then there is Chris Cummins again. He worked on program ML, which is based on GNNs. They are using for various applications. And then there is a CC compiler construction. They are using for graph representation for deep learning models of code, Stockman, etc. So we don't plan to cover it. So just one facet of this comparison, one facet is, for example, out of vocabulary. We begin at the beginning of the talk. We said that out of vocabulary it could be a problem. For example, NCC. This is one of the many metrics. We'll see more metrics in the next slide. But code to it has, though it's successful, etc. What happens is that out of vocabulary, well, the characteristics that could be further improved. And NCC, neural code comprehension, that has these are the out of vocabulary characteristics. And then our IR2VEC, it has no out of vocabulary. Now we saw this comparison of various models. We saw this plot earlier in this. Sandhya, or Naresh, can I go further? I barely have around 5 or 6 minutes.
No, please go ahead. Like, I mean, we can adjust in the following time frame. So go ahead, Ramesh.
Thank you. So we saw this plot early in this thing, and then in this talk we saw that it turns out that deep tune and Coden and deep tune we didn't cover in this talk. So DD will cover it, but Coden and we covered it. It is primarily based on lexical tokens. It's a very simple program analysis, but it requires a lot of training. And then there is Code to Vec, Code to Seek from Israel, Technion. They are broadly based on UST. And you have next we have these NCC and IR2VEC. They are based on information representation, and NCC a little more, little. It doesn't depend on the it doesn't use much of program analysis information, but IR2VEC uses this. So they both are here. So what you call we can do a brief summary of these various models. We can have OOV characteristics, size of vocabulary, the training time, embeddings, etc., etc. So Code to Vec, what you call, it faces OOV problem. So it is trained on 12 million AST pass, etc. And size of vocabulary is pretty large. It's 1.5 million token embeddings. And then it takes 1.5 days of training time. And then the embeddings, they are application specific. Red is bad, what called tick marks, etc., etc. There's some encoding here. You can have NCC, what call their Nurips work from ETS Zurich. They are based on IR, and what call 8.5K statement embeddings. So vocabulary training, it takes 8 days, and then while the task takes 10 hours, and then it's an application independent encoding. And we get to deep tune the classic PAKDD paper from Chris Cummins. It's a hybrid approach. It's a hybrid approach because they primarily rely on lexical tokens, but they use something very cute and very nice that really makes them jump. Obviate the OOV problem. So they don't face any OOV issue. And then their size of vocabulary is very impressive, just 128 tokens and characters. And then they have a vocabulary, they have a task, training time for task is around 10 hours in the application, but it turns out that it's application specific. Our IR2VEC is based on entity, so it doesn't face any OOV problem. It uses only 64 entity embeddings. And vocabulary training, it takes around 20 minutes, and then for the task on which we have published, it is just around 5 seconds. And there's an application independent encoding. These are some of the facets of comparison of various works, and since it's natural to play, I mean, this is not unbiased comparison, but there are, you can see the various features in all these works. So there is a trade-off in various encoding. So that brings to the end of this talk. You are more than welcome to visit us at compilers.csc.it.ac.in. There is an IR2Vec page there, and we also have a GitHub. We have open sourced our work, and you can see. Okay, so that's it. Thank you very much. That's it, Sandhya. Thank you.
Yeah, thank you, Dr. Ramakrishna, for deep diving into the source code, I mean, to the models for and the embedding representations for code. If there are any questions for Dr. Ramakrishna or the earlier part of my introduction, please, I mean, go ahead. Otherwise, we can go with a 5-minute short break and then proceed with Dr. Dibendu Das presenting on the compiler optimizations and deep learning techniques. I don't see any specific questions on the chat channel. So I would suggest that let's have a short 5 minutes break, and we will convene back at 11:36, if that is okay with everyone.
Yeah, I think that sounds good. So we'll take a break of 5 minutes and then we'll come back at 11:36.
Thank you, Dr. Naresh.
Thanks, Dr. Ramakrishna. It was very interesting talk.
Thank you, Naresh. Thank you, Dr.
Sandhya, I will be sharing the screen. Just have a look.
Yes.
Did I stop sharing screen or did I screen? I should stop sharing screen. Oh, yeah.
Yes, Didi, I can see your screen.
Okay, fine. Yeah, just let me know when to start and I'll go.
Sure, sure. Thank you. Actually, I did see one question at the chat window just now. So maybe we can, I mean, if Ramakrishna is still online, we can take the question, or once we are back from the, maybe like it's better to take it after we are back from the break.
Yeah, or maybe it's good to answer because
Ramakrishna, are you online?
person can view.
Ramakrishna, Dr. Ramakrishna?
Yeah, I'm here. I'm here. One minute.
So we have one question on the chat channel. Let me just repeat the question. I think this is with respect to learning the representation. So the question is, can we use transfer learning here? Can we train a model for C and fine tune it and later use it for Python, or even between different variants of Python like Python 2 and Python 3?
The answer is yes. Yes, and it's a very important thought and very interesting thought. Yes, you are right. What call for this? As far as I know, the what call creating this what call training data set is very important, and automatic migration from Python 2 to Python 3 is what you can also be done. And then you really wanted to use it for C and Python as well. So I think that it's possible. We haven't tried it, but there was a Facebook paper. Was it Glow or Aroma? I think they did something very nice on Python. You may want to look at that. But it's a very good question. Last year I think it was published in Uppsala. Maybe it was a really knows it. It's a good question.
Thank you, Dr. Ramakrishna. Thank you, Mr. Soham Ghosh, for the question.
Thank you.
Naresh, Sandhya, it's 11:37. Shall we start or?
Sorry, I mean, I just took one extra minute because we had that question answering. I think Naresh, can we go ahead? I mean, in the interest, like, I mean, we'll have to wind up at 1:30.
Yeah, let's continue. Yeah.
Okay, thanks, Naresh. So good morning to all of you, and especially the participants. Thanks for joining in. And my name is Dibyendu Das, and I work for Intel Savannah Labs, mainly looking at compiler optimizations for its various deep learning frameworks. And I would also like to thank the PAKDD organizers for giving us a chance to present this. As many of you know, this is actually a very, very new area. It's almost all research-based right now. Not many commercial, not even research compilers are built on this kind of frameworks. So it's very exciting for all of us to share this very initial and budding area to all of you, so that maybe you can get interested and start contributing to this space and take it to the next level. So thanks also to Dr. Sandhya and Dr. Ramakrishna for the wonderful presentations up till now. And the stage is really set for us to look into some of the deep learning-based compiler optimizations that have caught our interest in the recent past. So the agenda for today, for the next hour or so, I'll give once again a brief background into compiler optimization. You saw a lot about the IR, how the LLVM instructions look inside once it is lowered from your front ends. But I'll look a bit deeper into how these are getting used. Some of these use the techniques that Professor Ramakrishna mentioned. Some of them are slightly different, but today I'll mainly be talking about 4 different optimizations. One is deep tune that Dr. Ramakrishna referred to several times, with an end-to-end deep learning of the optimization heuristics, specifically for device mapping. I'll also talk about Ithamal, which is a basic block throughput prediction mechanism, which was pioneered by Professor Amar Singh and his student Charit Mendes from MIT. Deep tune is from Chris Cummins from University of Edinburgh. A graph coloring based register allocation, which is our work for doing register allocation. And then compiler auto-vectorization using imitation learning, once again from Charit and Professor Amar Singh. And then I'll talk about my view of things in this space and what we can see going forward. Okay, so Ramakrishna talked about several things, and out of that came one particular stuff is, if you look how programs get compiled, for many of you who are familiar with compilers, you may know, for many who are not, once the front end generates the IR or the intermediate representation, it goes through several phases, or what we call in the compiler terminology as passes. So we have this pass mechanism. So what is this pass mechanism? So this pass mechanism is nothing else but a couplet of an analysis and a transformation phase. So what we do is we take the IR, we analyze, okay, can we do this particular optimization? Is it fair to do this? It is correct to do it? Is it profitable to do it? And when you answer all of them as yes, more or less, in many cases, we go ahead and do the transformation. So analysis part is crucial. If the analysis says no, the transformation part will not take effect. Okay. So this group of an analyze pass and a transform pass is very, very important in the compiler domain. And you have these kind of passes stacked one after another. So you do X, you do Y, you do Z, and you do it in a certain order. Finally, you come to the end of your optimizations, and then you generate your target language, which is your machine language. So this is the usual flow. And today we'll see how we are trying to modify some of the traditional flows of the compilers. Now, many of you may know that lots of these compiler optimization depend on these carefully constructed heuristics. And what do you mean by carefully constructed heuristics? We mean that the compiler writers over many, many years, let's say you take a commercial compiler like the Intel's compiler, or a very well-known open source compiler like GCC or LLVM, there is a certain order which optimizations are applied. You will apply certain things like, let's say we normalize the loops, and then we do certain loop optimizations, or we apply inlining, and then we will do some common sub-exponent elimination, or things like that. Why is it important? Because this order allows you to optimize your code better. And how has it been derived? And it has been derived by, many trials and errors and many tens of years of expertise from a lot of compiler writers, both in the academia as well as in the industry. So as I said, like if you are inlining, like it's a very well-known compiler optimization. Which functions to inline? I know you say function to inline, which means that you have a function call from foo to bar. So instead of actually making the call to bar, I will push the body of bar inside foo. It helps in many ways. It reduces the call overhead. It may allow you to optimize your code better because you can now pass constants among certain things and optimize and things like that. So the question arises, like there are famous heuristics on which functions, because they're all hard problems, as Professor Ramakrishna mentioned, either NP hard or NP complete. So you're like really need to depend on heuristics. So which functions to inline? I mean, should I inline A? Should I inline B, or should I not inline any of them? Even if you know if you have to inline A and B, which order should I inline? Should I inline A first and B first? There are so many questions. Similarly, open questions regarding scheduling and register allocation. Like, as you know, all machines have a restricted number of registers, and you cannot keep all your variables which are being brought from memory into your register. That will be ideal, but that cannot happen. So you have to allocate some variable in registers and keep some of them in memory, and keep pushing and popping them from time to time. So how do you do it best? Similarly, like scheduling, like if you have a set of machine instructions, then what is the best order you should put the machine instruction? Because that will depend a lot on the architecture, and that will also lead to your effect on the actual runtime of your code. Similarly, like loop unrolling. And if I know I have to unroll a loop, how much should I unroll it by? Should I unroll by 2, by 4, by 8? Fully unroll it if I know the bounds and things like that. So many questions which are answered by compiler developers and writers using carefully constructed heuristics over the years. They run benchmarks, they run application code, they run customer code, and so on and so forth. And then finally arrive like, okay, looks like this is the set of heuristics we should apply. And then these heuristics go through certain modifications or changes from generation of hardware to generation. For example, if I take Intel's hardware, when I go from Skylake to Cascade Lake to Ice Lake to the tomorrow's Sapphire Rapids, because of the subtle changes in architecture, these heuristics also need to change. For example, if my cache size changes, a lot of these heuristics will need to take effect of that and model the new cache sizes or the new cache architecture so that I can do things better. So this is how the traditional compiler has been developed, and even today that's how it works. And these are all maintained by compiler engineers. And as you know, compiler engineers are very hard to come by. It's a very niche area and very difficult to train them. So this is not a scalable model. Like if you have a new algorithm to adopt, if you need to modify heuristics, it's not scalable. We do not get time. We do not get sufficient number of people to work on. Also, the adaptation to hardware is not easy, as I said earlier. I mean, let's say if you go from one hardware architecture to a new one, for example, let's say ARM, if you take ARM has its vectorization module, and now they support what are called a scalable vector engine. That is, you can have vector sizes go all the way from 128 to 2048 bits. So this kind of drastic change your hardware can cause a lot of difficulty for the compiler writer. It takes a lot of time to rewrite their passes, test them and bring them out for in a real market. And as you may know, people who use or the user of the compiler don't expect the compilers to fail. I mean, compiler is almost like you just expect it to work almost under all circumstances. So pushing the compiler engineers in the forefront for doing all of this work make the compiler development pretty fragile in many cases. Also, the space of possible optimizations that are there, we really cannot, as compiler writers, we really cannot explore them because, our time is limited, our thought processes are limited, our timing for, release of certain compilers aligned to certain hardwares is limited. So as a result, people have found out that many compiler optimizations are either out of date. We are still using, things that have been written 10 years back and have not been tuned at all for the modern hardware. right? So things like that. These are the challenges people face while doing the traditional compiler optimizations. So what would the modern compiler writers would like to do? I mean, definitely heuristics cannot be replaced easily because these have been tuned for many, many years. But what you also want to do is we want to execute faster. We want smaller code footprint, right? We want to reduce power, and there are so many vectors to look at. It's not very easy for the compiler writer to explore all of them. So here comes machine learning to the rescue. And it's not that machine learning has been thought of in the compiler space of late. There has been work going back all the way to the early 2000s and all that, where people have tried to use machine learning for various things, including something like, say, loop unrolling. But the earlier work, as many of you know, concentrated on feature engineering. For example, Ramakrishna was talking about the IRs and the control flow graph and the data flow graph and things like that. So if you look at, let's say you have a for loop which has some kind of a data flow structure like that, and I want to know how much should I unroll it by? Should I even unroll it or not? And so what the feature engineering used to do is, you would extract, okay, how many instructions are there in the loop? Are there load instructions? Are there store instructions? Are there branch? Am I going to have a cache miss? What's the probability of a cache miss? Are there control flow? Things like that. So you will collect those information as special features, and then you will train this. You have your training programs with the features extracted from these kind of loops, and then you have a supervised machine learner. In many cases, it used to be a decision tree or SVMs or gradient boosting models and things like that. And then once you have that kind of a learned model, you will apply it when you are deploying it for your new program. So you can look at some of these older or traditional machine learning techniques in this well-known work. It actually looks at a whole gamut of machine learning compiler optimization over the last, let's say, 15, 20 years by Wang and Michael Boyle. So if you look at it, yes, many of these were not bad, could have been applied, but if I look at it as a compiler writer today, even in a very well-known compiler like LLVM, hardly any of these techniques have been adopted. For many various reasons. One is feature engineering is hard. You really don't know all these things. Extracting this, keeping it up to date may have a lot of issues. So that's why we are trying to go to more recent advances with deep learning, where we can extract things automatically. We don't have to go and depend on feature engineering, etc. Okay. So that gives you a very, very top level view of what the compiler optimizations look like and what are the challenges that the compiler writers of today face while doing this kind of compiler optimizations, and how now we can try to apply or think, because many of these optimizations are still hard to do because correctness is a major issue. So we'll see some of the challenges now. So I'll talk first about deep tune and about the end-to-end deep learning heuristics. This was work done by Chris Cummins. Okay. So deep tune, what is deep tune? Deep tune is mainly end-to-end framework, which actually takes in OpenCL code. For folks who do not know what OpenCL is is like CUDA, but it's open source. And people usually write OpenCL code for codes to be mapped to the GPUs. But what people have found, just not OpenCL or in CUDA also, if your code is very branchy or there are certain characteristics of the code, sometimes the OpenCL code really doesn't run very well on the GPU. Okay, and maybe actually it runs pretty well on the CPU. So the question that Chris and his team tried to answer is, given a piece of OpenCL code, should you actually run the code on your CPU or should you actually run the code on the GPU, right? And the way they do it is, by some of the techniques that Professor Ramakrishna mentioned, but this is really an end-to-end mechanism. Okay. So what are the components of deep tune? So I've shown you a very concise picture of what the actual deep tune flow looks like, and then I'll go into the bit of details. So if you look in deep tune, the source code, which is written in OpenCL, There's a module called a source rewriter, which is nothing else but some kind of a normalization of the tokens. Then you have an encoder, followed by an embedding model, followed by some LSTM layers. And then you also have some auxiliary inputs. These are nothing else but inputs which give some idea about what your hardware is. It is a CPU, GPU, some characteristics of your hardware. And these inputs from the LSTM and the auxiliary are concatenated, and you have a batch norm followed by some dense neural net layers, and then we get a 0-1 prediction for a CPU or a GPU. All right. Now, if you look at the language model, as I told you, this is how an OpenCL kernel looks like. Okay, so there'll be keyword called __ kernel, which means that there's an OpenCL kernel, and you'll see some terms which you don't usually see in normal C or C++ called global, locals, get global ID. You know, these are specific to the GPU terminology. We didn't really need to bother about that, but let's say, you know, this is an OpenCL kernel, and what you do is once you see this kernel, you use the source rewriter to normalize this kernel in a certain way. So what we do is, let's say the name of the memset kernel is not very important. The exact names of your parameters are not very important. So what they do is, you know, these names are replaced by certain characters like a, small b, small c, etc. And the variable names are also changed so that the main thing you are focusing on is the semantics of your code and how the code is getting written instead of your variable names or things like that. Because see here, this is not like, you know, there are machine learning systems where you try to predict what will be a good variable name and things like that. So here we are not interested. So we kind of drop all those information, kind of generalize it so that all code with similar kind of structure look almost the same. And once you do a source rewriting, you do a sequence encoding, which is a simple index-based encoding. So for example, the keyword __ kernel gets the index 1, space gets an index 2, void gets index 3, and so on. So these are the first three you know, layers. And as Professor Ramakrishna mentioned, that I think they use of the order of some 128 you know, tokens, and they are able to cover the space of OpenCL kernels that they are handling today. Now, if you look into the other phases, right, after the encoder comes the embedding. Now, if you look at the encoder, because it is index-based, it is a sparse representation, so we really don't want such sparse representations. We want to convert it to a dense representation, so you use an embedding layer, and the output of the embedding layer is of size 64. Okay, so you do that, and then what you have is a 2-layer LSTM, okay, with once again the 64 hidden layers inside each LSTM. And once you come out of that LSTM, you have again 2 dense layers coming out of that, and the auxiliary inputs are now taken out. So once you come out of the LSTM, you concatenate your auxiliary inputs along with that. And then you apply your couple of dense layers, which is the dense NN that you see here. And finally, you have your output, which is a value of 0 or 1, right? So this is the whole model, which is end to end. It takes the OpenCL code as your input, uses the lexical tokens mainly for your encoding. Does a 64 way encoding of embedding of your of those encoded tokens. Use an LSTM, some amount of batch norm and auxiliary inputs, which are, you know, for GPUs it will be work group size and data size. If you are familiar with those terms, for CPUs it will be general characteristics about the CPUs, and then, you know, out comes finally your predicted optimization in terms of a value of 0 or 1. And the code is there in this particular link. So if you are interested, please have a look. Pretty simple code, and you can run it. So visualizing DeepTune, as Professor Ramakrishna was showing earlier, right, with their clustering of the various tokens. Similarly, You know, in the paper, Chris and others show the kind of clustering they achieved. And if you look at it, you can see that the clustering may not be as good as what we see in IR2VEC, and we'll show the results why. Because it is learned end to end, and we are just taking on lexical tokens. We are not taking care of control flow or data flow like IR2VEC, because it's slightly earlier work and a much more simpler encoding. And then what we see is that the activations in the dense NN layer, they vary quite a bit depending on what kind of hardware is used. And that's also expected because we are feeding the details about the hardware. For example, here, these are the names of several GPUs that you may be aware of from the AMD and from NVIDIA. And they will have different hardware characteristics. And depending on that, we'll also have different activations. And the outputs will also be different. Okay. If you look at performance for this work, they actually compared this work with two other work. One is called optimal static mapping, which is nothing else but, hey, for a large class of kernels, is CPU mapping better or GPU mapping better? They just run it and then say, okay, GPU is better. So just use GPU as a mapping, or say CPU is better, I'll use CPU as a mapping. So that achieves only about 58% accuracy over all these various benchmarks that they ran. Grew et al. So this is an earlier work which uses similar to that feature engineering. They had handcrafted features and a decision tree model that achieves about 73%. But DeepTune was able to use this kind of a predictive model, using LSTM and lexical token encoding, and achieves an accuracy of about 84%, which is pretty impressive. And I also wanted to show you one slide from IR2VEC because Professor Ramakrishna's paper, which followed this paper, actually did a comparison. And what they show, if you look at, let's say, DeepTune, which is here, this is one of the AMD hardware, and this is one of the NVIDIA hardware. If you look at IR2VEC, both symbolic and flow-aware, they actually do quite better compared to the DeepTune because of their more complex and more comprehensive modeling of the IR. So that's in brief is the first optimization that I wanted to tell you about. It was very well received at that point of time because it's kind of a first paper which looked at a kind of this end-to-end and stuff. So now I'll switch gear a bit and look into slightly different optimization from the back end, mainly from the assembly language perspective. And this work was called Ithamal, and this is mainly for basic block throughput prediction. And for folks who are familiar with x86, this is the kind of x86 code you may have. And there are various reasons why we may want to predict how much a bunch of x86 instructions will take in executing on a given piece of hardware, right? So for example, on an Intel Xeon platform, this piece of hardware may take 40 cycles, this may take 44 cycles, and this may take 36 cycles in terms of clock cycles of your CPU. And the reason why people want to study it is they want to compare various hardwares. That's one. They may also, while they're building their new hardware, they want to see where they can improve stuff. Folks who are doing performance optimizations on the compiler side, on the modeling side, are interested to know about this particular number. So it's a very important problem for both computer architects and system architects to see how much time a certain block of x86 instruction is taking. And here we'll restrict ourselves to basic blocks, as Ramakrishna mentioned earlier. And basic blocks is just a single linear code flow. You can only come in at the top and come out at the bottom, and you cannot jump in or jump out at the middle anywhere. There are already several analytical models available from LLVM itself called the LLVM MCA, which is LLVM's architecture analyzer, machine code analyzer. From Intel, it's called Intel ACA, Intel Architecture Code Analyzer, and so on. So they all do a decent job, but what this by Amar Singh and Mendes, so they found out that we can do much better using newer techniques from the deep learning model. So why also the fact that, accurate modeling of processor core is extremely complex. So this is one of our latest from Intel. This is the Cascade Lake core block diagram. And people who are familiar with architecture would know that there are front ends, there are branch prediction units, there's micro up cache, there are, schedulers, there are load store units, retire units, and like several thousands pages of specification for the core. And if you really want to model, and these are outer order machines, these are not in order machines. To model this is really, really complicated, and you're definitely going to miss certain details and features of modeling when you are trying to write really a model in your code and then trying to run them. Okay, so the idea is, okay, I have a bunch of instructions, it goes through a Cascade Lake core, what's the kind of cycles that it's supposed to take. And so, as we said, that, very easy to omit details, very, very easy for the folks who are developing the model, very easy to omit details. Specs are inaccurate. Sometimes people have figured out, there are issues with specs. Some details are proprietary. For example, if LLVM MCA is building a tool, it is an open source tool, but I need to know everything about, let's say, the Cascade Lake core, and some of the details may not be even known outside Intel. So that makes it incomplete to some extent. So what is the high-level view for their work? So the high-level view is, okay, we take a data-driven approach. We have this data set, which is like from spec benchmarks, from NAS benchmarks, from other open source benchmarks. They collected like several million basic blocks of instructions of this form. And for them, they have this ground truth by running them on actual. So these are not very, very big, because in general, assembly basic blocks are not very big. Several tens of instructions, maybe sometimes running into hundreds. And then they actually run it on the real hardware to get your ground truth, like how many cycles are they really taking to execute. And then what you do is you have your neural net. I'll talk about what the details of the neural net is in the next slide. You have a neural net to learn that truth and the usual backprop and things like that. So this is the high level view. And the advantage of this approach is if you have really a good net which learns this, you can move from, let's say, from today's, from Cascade Lake to Ice Lake generation, or Ice Lake generation to the Sapphire Rapids very, very easily. You need to just retrain, okay, and maybe even do some amount of transfer learning, because maybe a large part of your architecture is still remaining the same, and things like that. So it's a model. You have to now rewrite, add all the new features, everything, and it takes a lot of time. So the way Charit and his team devised this is, once again, they are using LSTMs, and similar to what you saw with Chris's paper, but they are now using a two-layer LSTM. And the input is obviously not an IR anymore, or not an OpenCL lexical token. The inputs are instructions in assembly. For example, move ECX to 0, where ECX is a register, right, in your x86 code. And similarly, add EBX ECX, where these are registers in your x86 code. Okay, so these are first canonicalized. For example, the way the canonicalization works is you have your move, and then S will stand for your source, okay, which is your constant. So this instruction mainly means move the value, hex value of 0x02 to the ECX register. Okay, so destination register, which is canonicalized by D, is your ECX, and then this is your N token. Similarly, you see add. See here a lot of extra registers that have come in, right? This is your source, which is ECX, but you also see EBX, and there also you see EBX, because this is a kind of implicit registers that get used. When you say add EBX ECX, it means add EBX ECX and put the result back into EBX. So it's not like, you can write it as add EBX ECX, but people use a shorthand notation, and then you should be able to canonicalize it and make sure that this is what it means. Once it's canonicalized, okay, you do some similar like a one-hot encoding and do some kind of encoding for that. But then the embedding happens, and like in the previous work, the embedding happens along with your application. So these are specific, application-specific embeddings, and not application, embeddings which are not application aware in a way like what it happens in IR2Pack. So these are application-specific embeddings. So once you have the embeddings, these are the vector embeddings for each of your tokens, move, source, const, D, etc. We do the first layer of LSTM, and the first layer of LSTM is for each instruction. Okay, so the first layer of LSTM, let's say for this instruction, you have this layer of LSTM. Similarly, for this one, you have the layer of LSTM, and since the instruction size is usually not big, this LSTM may not have more than, let's say, 16 or 20 units or things like that, or maybe at most 32 units. So this is the first layer of LSTM for each instruction. And this each instruction LSTM's output, right, is now fed to the next layer of LSTM for your basic block. As you said, as you know, basic block consists of many instructions. So the first layer is your instruction layer for LSTM. And for each one, you'll get the hidden vector for the last output, right? So this is the HMoves output, this is the HADS output, and then it is fed to the next layer of LSTM, with each one standing for one instruction. So if you have, let's say, 20 instructions, you'll have 20 of these here. And so usually, once again, I think the kind of training set they probably had about 40, 50, 60, 70 instructions. So you probably would not need more than a 100 sequence LSTM for your final layer. And then it will go here and go through some kind of final layers and get your throughput prediction. So this number will be your throughput prediction once you give your instructions. And what they found was the ETML almost halves the error rate across multiple microarchitectures. So if you compare it with LLVM-CA or LLVM-ISCA, you see that while LLVM-MCA has about, let's say, 20% error rate, right? ISCA also has about 20% here, about 16% here. And this is coming actually from Intel, by the way. So Intel knows its processors so well, but still you see a 20% error rate or a 16% error rate. In comparison, a totally new data-driven model gives you an error rate only at the level of 7 or 8% for the entire corpus that they looked at, which is actually very nice and very interesting. So once again, the code for this is in this GitHub, and this is a PyTorch implementation. Feel free to have a look. So I'm doing on time. Okay, so I still have maybe about 15 minutes, 20 minutes. So the third one that I'm going to talk about is a technique which we developed for register allocation using the famous graph coloring algorithms. Okay. So many of you are already familiar with graph coloring. It's a very important problem in computer science, and it's just an assignment of labels or colors to your nodes such that if you have an edge, the two nodes at the end of the edge cannot have the same color, right? And the minimum number of colors that can be used to color this graph is called its chromatic number. So if you look at it, the chromatic number of this graph is 3 because you cannot color this graph using lesser than 3 colors. And what is this use in this register allocation problem? The graph coloring has been used in many heuristics in computer science, but what is used in the register allocation problem? So let's look at it. As I told you earlier, register allocation is a very important problem in compilers because we want to keep things not in memory, but in the register so that things become faster. I don't want to go to memory back and forth. I want to keep things in registers, but the number of registers is limited. You may have 32, 48, 64, even some embedded processors may have much lesser, 16 registers. So how do you fit stuff in? So you really cannot fit stuff in. It's as simple as that. So you need to do this, push and pop mechanism. So you keep some stuff in, push out, bring it in, and things like that. So how do you do all of these things? So here comes register allocation to the rescue. You have this concept of interference graph, and what does it mean? So once again, if you look at a basic block, this is once again an intermediate code, but at a slightly lower level called machine IR. So we're talking about IR, which is LLVM, but this is not LLVM IR. So once you are in the domain of register allocation and scheduling, you get into a slightly lower level IR, which is closer to the machine called the machine IR. So in LLVM, we have this x86 machine IR, and it may look something like this. You need not bother about the exact syntax, but you have your memory access, you have your usual operations and things like that. and you define some properties called live in and live out. Okay, and also some things called the live ranges. So what a live range means is from the time a variable gets defined to its last use is this live range. For example, if you look at G here, G is defined here, and its last use is in this instruction. After this, is not used. So this is the live range. So what does it, intuitively imply? It intuitively implies that if you put a variable in a register in this time frame, you can release that register for another variable after this. You need not keep it after this, which means that, okay, someone else can use it. It also means that if there is another live range which overlaps, you really cannot give them the same register. For example, G and J cannot be given the same register because then they will trash each other and give incorrect results. So you have to put them in different registers. So what you do is you have this kind of code, you have this kind of live range information, and you create what is called as the interference graph. So interference graph means that, let's say if you look at G, what are the other live ranges which, what are the other live ranges which has overlap with G? So at this point, you can see H has an overlap, J has an overlap, K has an overlap, and things like that. So I will draw this 3 edges between these 3 variables because I want to show that there's an overlap. And now if I get this interference graph and I can color it, okay, with the minimal number of colors, it will tell you how many registers will be required in the optimal case. And in many cases, what will happen is the number of registers will be less than that, in which case you have to do something called spilling, which is like push it to memory and again bring it back. If it is lesser than the number of registers you have, which is great, okay, then you can, at the very outset itself, you can say, hey, give F to this register, give G to this register, and so on and so forth, and you can run it optimally. Okay, so this is how it is in a model. So how did we model this whole thing? So we viewed the problem of graph coloring using sequence-to-sequence translation. And how does it look like? We actually said, let us take the adjacency matrix of this interference graph, and out of this will come the color assignment for each of its nodes. Okay, so this is how it has been modeled. And in between lies several layers of LSTM. And as I said, the adjacency matrix is the adjacency matrix for your interference graph. And then for each sequence, we take just the adjacency vector, encode that adjacency vector, and send it through this layer of LSTM. We have, for this particular case, we have 1024 hidden units and so on and so forth. Also, we trained this whole thing actually using a set of random graphs. We generated about 10,000 random graphs, and we got it optimally colored. We got it optimally colored for this 10,000 random graphs. Now, people may ask, like for large random graphs, it's very difficult to optimally color them. It will take a lot of time. But yes, because in the domain of register allocation, the sizes of the graphs are not huge. Usually it's like 100, 150, 200, usually less than that, maybe even 30s, 40s, 50s. So as long as we can color those graphs optimally, we can train them and then do inference from them. Now, if you have larger graphs, obviously you'll have problems getting the training set for optimal color allocation. So there are techniques for that. Have a look at the paper. We have told you some, said some things which can be done in those cases. There's a problem though, and this is what I alluded to earlier, that correctness is a very, very big issue in compilers. So many of the things that we were doing, we are not really talking about correctness, like whether we have to do prediction for running on CPU or GPU really doesn't bother about correctness. If you predict wrongly, you will get slightly lower runtimes, right? Let's say the second one that you talk, Ithamal, okay, even if you're wrong, yeah, your error rate will go up, but correctness will not be impacted. But this case, that's not true. If you incorrectly predict the colors, you are going to give maybe the same registers to 2 variables and all hell will break loose. So really, you cannot be incorrect here. And unfortunately, LSTMs and this mechanism have no way of encoding constraints to say that don't give and the same color to 2 nodes connected by an edge. What we came up with, so we came up with this hybrid concept. We said that let us train and let us do inference using this DL-based, LSTM-based, model. But at the end of the day, we are not sure if still the assignment is correct or not. So we have something called an error or color correction phase after we get our inference, okay? Because in some cases, what may happen that we will get what are called as invalid edges, which means that the colors are the same. And to give an example, this is a famous forest fire graph used in literature in many cases for graph coloring. It has a chromatic number of 5, which means it can be colored using 5 colors optimally. So if you use an LSTM-based model, what happens is the LSTM says, hey, it can be actually colored by 4 colors. Obviously, it's incorrect. We have 2 invalid edges for that. The invalid edges you can see here are written C to C3 and then C1 to C5, right? So these are the edges which are invalid. Now, what do we do in such a case? So we now apply a normal program. It's actually a very, very lazy and very simplistic algorithm, which is very greedy. So what I look at its neighbors. So I said, hey, both of them have got color 2, but I looked at neighbor of 5 and I said, okay, one of them has 1, one of them has 2. So there is already 3 and 4 available. So I can actually color it using 3 and break this invalidity. But when I go here, I see that if I try to put the same thing, it doesn't work because all the colors have been used up by its neighbors. I cannot put 2, I cannot put 1, I cannot put 5, I cannot put 4. Sorry, I cannot put 4, so I have to put a new color. So what happens with this color correction is you are either able to use one of the existing colors, or if not, in the worst case, you have to put new color. So what happens is as you put new colors, your solution deteriorates and it goes away further and further from the optimal. But in some cases, it doesn't. For example, here we are able to even get after correction also using 5 colors. Okay, so which is actually a very nice result. So in general, we see, when we tried with various kinds of graphs, we saw that in general, we may get up to about 20%, 25% of invalid edges, and we have to color correct them. But in general, we don't see using a lot of additional colors. We usually use about extra 2 colors or 3 colors from the optimal coloring. Some of the details are in the paper, and then if you look at how it is being used in LLVM's greedy register allocators, we have not really encoded it, but we kind of did it kind of outside. This is LLVM's greedy register allocator pass. I'll not get into all the details, but we do live interval analysis. We do some kind of spill weight calculation, as I said. We do register assignment, and then some other parts. And this is the normal flow. And what we do it from the live interval analysis, we take out the interference graph, fit to LSTM model, and get the color correction assignment, and we compare it with what the LLVM would have done, right? And we see that for several spec 2017 benchmarks, actually we are almost at par or doing better than what LLVM's greedy register allocator would have predicted should be the register allocation. But this is not embedded inside LLVM yet, so you will not be able to find code. So even though this code is here, this code is mainly to do your training and inference and show you how the coloring will work, but it is not actually embedded into our LLVM infrastructure. So Sandhya, I'm doing with respect to time. Do you have 10 minutes?
Yeah, I mean, actually, you can take 15 minutes, DD.
Okay.
So go ahead.
Okay, fine. So anyway, I'm on the last optimization till now. If you guys have followed, we have outlined 3 different kinds of optimization. One is an end-to-end predicting whether we should place our kernel on the CPU or GPU. One, given a set of assembly instructions, it predicts how many cycles it will take on your hardware. And the third one actually tells you how to do your register allocation, just not how many registers you will use, but how to even do your register allocation and the assignment for that using deep learning techniques. The third one, so all of them, if you look at it, coincidentally used LSTM, but LSTMs, as I said, have problems in terms of encoding constraints, right? So people have been, because many of these compiler optimization passes, especially on the analysis side of it, would require, and transformation side, would require correct transforms to happen. So people are moving towards a kind of reinforcement learning-based approach, because there you can have valid movement between states. You can stop invalid transformations, and in general you can enforce your constraints much better. Okay, so I'll talk about one of those reinforcement learning techniques. I'll not go into great detail because it's a slightly more involved paper than the other 3. So once again, this work has been done by Charit and Professor Amar Singh, and I think it was published in NeurIPS about a couple of years back. So what is the idea? So first of all, if you are not familiar, let me tell you what auto-vectorization is. So auto-vectorization is nothing else but, in general, you have scalar code, but in the hardware, you also have vector units. What are vector units? That it can do many scalar operations at the same time. Let's say your scalar register is 64 bits wide. Your vector register in general will be like a 256 bit wide. So you can do 4 vector operations, 4 scalar operations at the same time in that vector register. So this is called vectorization. So this mainly, you can think of it as widening of your scalar to wider type. So mostly people understand vectorization in terms of loops. For example, if you have loops, you have arrays, you are striding over arrays, and let's say instead of executing one element of the array each time, I can do 4 elements of the array together, 8 elements of the array together, 16 elements of the array together, depending on your hardware capabilities. So that is called auto-vectorization, and in general, loop vectorization. But in this particular piece of work, Saman and Charit actually tried to handle what is called as superword level parallelism, which is a slightly more unrestrained or unconstrained version of loop vectorization, where they try to vectorize straight line code. So you don't need to have loops. For example, if you look at this code, and if I have a vector register which can handle 2 elements together, I can actually do, instead of doing these 2 separately, I can do A1 to B1 together in one single vector register. Okay, so this is the vector code. Okay, and so this the superword level parallelism problem. It's a superset of loop vectorization, and it's actually a very hard problem because you need to know what is called as optimal packing. You need to know, like, should I pack A1 with A2, or should I pack A1 with A3? Should I pack A1 with A4? And so on, and because of various profitability reasons and things like that. And as you go further, how do you keep on increasing your packets? So if you do a naive, ML strategy, what can happen? Let's say you really don't understand everything about the correctness. You somehow try to pack A4 and A5. And you see immediately that's going to be wrong, because one of them is a plus operation and the other is a multiply operation. You really cannot pack them together, because for SLP vectorization, you will need what are called as isomorphic operations. That is, you should have similar kind of memory access. You should have the same operator working on it. Because once I give a vector register, I cannot do partially vector registered using, add and multiply and things like that. There are some special, instructions that can that will allow you. In general, hardware will not allow you that. So this will not be, let's say, allowed. So in which case, your neural machine translations should stop this kind of naive, incorrect strategies. So here comes the very well-known Markov decision process problem and the formulation of that. So what we do is we present the problem as a Markov decision process problem, and where each state is your current state of how much of it is packed and how much of it is unpacked. So if you look at this current state, right, nothing is packed, and then you can take one of these valid actions. That is, you can either pack A1, A2, or you can pack A2, A3, or you can pack A3, A4. There may be reason like why you are not packing A1, A3 or A1, A4. I mean, these are valid. Okay, I understand A1, A5 may not be valid. So currently, we have not shown that, because if two memory accesses are not contiguous, you may pay a high penalty in bringing them together into your vector register. But in general, all those also will be valid actions. It's not that they're invalid. They'll also be valid actions, will also be considered. Now, let's say after this, you go to a state where A1 and 2 are already now packed. Now, from this state, I want to go to another state where now A3 and A4 will be packed. So you can see that the state formulation happening by looking at your currently packed data and the currently unpacked data, and making a valid jump to a new state and getting the reward functions and the values for that, and iterating over this whole thing. And the pairwise instruction packing problem can actually be posed both as a top-down problem or a bottom-up problem. So you can pack coming from top to down, or you can pack going from bottom to up. In the paper, they showed that it's slightly more advantageous coming from top to down, but maybe in some cases the other way will work better. There's some details of how the state looks like. I'll not go into all the details, but if you look at inside, of the MDP, how they have really represented the MDP state, they have quite a bit of details in terms of not only which, let's say, this is your code, A1, A2, A3, A1 can be packed with A2, A1 can be packed with A3, A2 can be packed with A3, and so on. There are also some other information in terms of what are your dependency edges, right? Like, with respect to position 1, with respect to position 2, what are your possible packages? What is something is called a focus edge? That means you start looking from that node onwards. So it's a kind of implementation detail which you'll find in the paper, but basically this is a slightly higher level view, slightly lower level view of what goes on inside your MDP state. Okay, and then comes the idea of imitation learning. Now, in this case, what are we really imitating? Now, there is a older paper from the same guys about 2 years back where they solved the same problem using ILP solvers, right? Because this is a hard problem to solve, and these are like how to pack two instructions together. They solved it using ILP solvers. And what they're trying to do is once they want to go from one state to another, they want to actually mimic that transition of the ILP solvers. So that's how it is trained. It's trained by mimicking that ILP solver. And that ILP solver actually works as your oracle. So the Go SLP is their earlier paper which uses that ILP solver. And that will be like your policy decisions, right? From one MDP state to another, what are your policy decisions? And that policy decisions will be handled by a graded graph neural net. So what they will do is each state, as I showed you earlier with this kind of a graph, is actually modeled as a GNN. So this will be modeled as a GNN, okay, with these as your graph nodes and the whole thing as your graph neural net. And on that GNN, the training should tell you the probabilities of your valid actions based on the imitation of this oracle. So once you get the probabilities of the valid action, you take the ones which will probably give you the best reward and so on and so forth. Okay. So yeah, so that kind of completes this. They also showed, once again, I'm not showing you the data for that. So they also showed that they, I think, beat LLVM's current algorithm in several cases and do very well compared to that, because you can see that ILP solver is actually an exact solution. But the thing is, ILP solvers take a lot of time because solving things exactly will take a lot of time. And if you want to use ILP solvers in real commercial and compilers, it really becomes a big problem. In general, people will not usually use ILP solvers in real compilers. It takes a lot of time. So instead of that, if you use this kind of techniques, you probably will go much faster. Some other work we did not cover, which are also pretty important and have been getting some prominence of late. One is static neural compiler optimization via deep reinforcement learning by Mamdil et al. Recently published in Supercomputing 2020, which tries to solve. We're talking about the phase ordering problem or pass ordering. Should you do pass A before B, C before D, D before something else? That's a well-known open problem, and they have tried to attack that problem using deep reinforcement learning, especially using the LLVM compiler pass pipeline. And a similar work like the imitation learning is once again end-to-end vectorization with deep reinforcement learning, mainly for loop vectorization. But this really is slightly different in the sense that it tries to predict the most beneficial vectorization factor. When you mean vectorization factor, it means that should I vectorize 2 elements? Should I vectorize 4 elements? Should I vectorize 8 elements? Provided that your hardware allows all these options. And one of the latest papers, I don't know whether it has got published yet, but is at least in archive from the Google guys, called MLGo, where they are tackling a very, very important and very tough problem of trying to inline using machine learning, reinforcement learning specifically, but this is a slightly constrained problem because they are just inlining for size. That means once you inline, usually your code bloat will happen because you are inlining a lot of code inside, like, it's getting bloated. So they want to inline for size in the sense that inline it, but only, allow very small amount of code bloat. So, that's a slightly different problem. In addition, now you have a compiler Jim from Facebook AI, which is once again, Chris actually finished his PhD and joined Facebook. So he's trying to, popularize this. And it will be kind of a toolkit where you can use some of the techniques as a kind of service for driving optimizations in the compilers. So yeah, finally wrapping it up. So what are the conclusions and future directions? So as I said, the whole this whole series of lectures actually, and even especially this part, we are at a very early phase. We are just at the cusp of utilizing these techniques for compiler-assisted transformation. So the big challenge, as I said, is to ensure correctness of the transform code. Some of the work we saw proposed NLP-like techniques like LSTMs and so on. Some of them are proposing reinforcement learning. Also, no consensus yet on standardized program representations. You saw Professor Ramakrishna present various mechanisms. But is IR2 vec better? Will something else come up? We still need to see. Maybe something different may work better for your particular problem at hand and things like that. Also, no consensus yet on how to represent control and data flow in your code. Should you use data flow representation? Should you use graph neural net? Should you use a simple sequential mechanism like we saw in Ethamal? Those questions are also open. So as I said, through the compiler GM and other stuff, Cummins and Hugh Leather, they are suggesting optimization as a service. So in their thought process, mostly all of the optimizations will probably be RL based, and you will just be calling that and using it as a service for your particular downstream optimization or task that you are designing for your compiler. So this is a personal opinion. Don't take it too seriously. It's a bit of salt. I think RL may turn out to be too costly to be introduced for our optimization process. So as many of you know who are RL experts, that it is heavy on resources, both on the hardware resources, software resources, power, machines, etc. So that's an issue. Compile time may blow up heavily. We cannot afford to compile. Let's say LLVM today, if you use LLVM's native build, it probably takes about 8 to 10 minutes to get the full LLVM compiler itself built using GCC or LLVM. So if you are using this kind of stuff, let's say it goes up to hours, it will not be acceptable. People will not accept that. So maybe in my case, in my thought process, I'm thinking that it will be a mix. Some optimizations, easy ones, maybe NLP-like, where correctness may not be a major issue. The other ones, the important ones where correctness is an issue, will probably take our models. Also, the question remains that even for the models which, for example, the way we developed one hybrid model using a DL and a fast correction algorithm, would we see more of this kind of models in the future where we really would not get an explicitly correct output from our model, but then we can do a small tweaking pass at the end and do a fast correction and correct the algorithm without really going through much more complicated models. And then obviously, I developed this model for, let's say, Intel hardware or Habana hardware or some other hardware. Can some other compiler take it easily? Will you be able to do transfer learning of this easily? We take it across compilers, across hardware, how all of those things will look like. And so, in the future, there's still a question mark. I started with this diagram. I want to end with this diagram that we had this analysis pass and we had a transformation pass. Then in the future, will these just become a learned analysis model and a learned transformation model? And then, maybe in our lifetime, if we are lucky, we'll see some of those happening. If not full, we may have a series of learned analysis model and transformation model, and then a final code generation. So with that, I'll end my talk, and I can take a few questions, maybe a couple if there is time, and then I'll hand it over to Dr. Sandhya. Thank you.
Dr. Dibyendu, thank you. We have one question on the chat window. So the question was like, I mean, you had mentioned the use of LSTM models for some of those compiler use cases. So the question was, has there been use of transformer-based models for some of these problems, such as, I mean, basic block throughput prediction or mapping between CPU to GPU and so on?
No, not yet. We haven't seen, but maybe people have applied and they have not published, because, as I said, these are all like last 2-3 years paper. Yeah, I mean, people, if they apply those kind of models, you may see some accuracy improvements and things like that. So yeah, I mean, I'll suggest that that's also one of the reasons we are having this particular session, that please feel free to experiment with them. But as far as I know, there are not results using transformers right now. Something I think with attention, I think Professor Ramakrishna presented on the code to vec kind of things, but especially on the deep learning side, people have used a lot of graph neural nets. Not much of attention, but please feel free to take this code, maybe change them and try attention and try things and see whether the performance improves.
Thank you, Dr. Dibyendu. I suggest that we take a short 5 minutes break and then come back and do the last session on DL4Code applications. So we will convene back at 12:43 or so. Would that be okay?
Yeah, let's do that, Sandhya. I think Naresh may be on mute.
Sure, thanks. Folks, in the interest of time, I was thinking like maybe we can get started on this final session of this tutorial, if it's okay with everyone. I guess Naresh is away, I mean, probably, so.
Yeah, let's start. Yeah.
Let's start, I guess. Okay. So the final session of this tutorial would be around like how deep learning techniques can be applied to different applications for software engineering. In particular, like, I mean, as we saw earlier, big code use cases can be very widely different, right from learning coding conventions to all the way to comment generation, code summarization, or even like, I mean, automatic code generation, right? So when you think about like building smart software engineering tools, there are a bunch of use cases. However, we would be getting into a little bit deeper on few of these use cases. We would look at how can we find software related bugs automatically, then look at a paper which talks about how these bugs can be fixed automatically, and briefly touch upon like, I mean, how can we do code search using DL4Code techniques and also doing code clone detection. So, I mean, the first step is to start with is like, I mean, given a piece of software, can we find out like whether the code has any bugs automatically, right? This is an important problem because I mean, a lot of time is spent on software maintenance or like identifying bugs, and building a deep learning technique which can automatically find bugs is very significant from the software engineering perspective, because it's going to improve programmer productivity. Right. Before we actually get into any specific DL4Code application, the way I would like to frame a kind of mental model or approach to DL4Code application is the following. For any of the software engineering problem, the first step is to figure out, can we find an analogous use case in standard natural language processing? Right. So if you want to say we want to identify between, say, a buggy code and a correct code in software, what would be the equivalent or analogous problem in standard NLP? right? So if you think about it, in standard natural language processing techniques, there have been tools and systems which have been used to identify errors either in spelling or in words or in syntax or semantics of the language itself, right? So what we call as error detection in text. I mean, and this is a very common thing, right? I mean, you would have seen uses of this in any word editor program, like a spell checker, which reports this is probably an error. And there are also like grammatical errors that get detected by many of the editors, right, for the normal human language text. So the analogous problem would be like, how do we identify like errors in the code, which essentially means that given a, I mean, if you think in terms of standard NLP, given an English sentence or some language in some human language, say English, Chinese, or Arabic, can I classify it as correct or buggy, right? So this means that detecting bugs can be modeled as a text classification problem, and that too as a text classification problem, which is two-class classification, with one class being buggy, the other being correct, right? So the moment we model this as a text classification problem, we can think about applying any of the models or any of the wide amount of research that's available under text classification to finding bugs, right? So once we do that, what are the two other questions that become significant? The first question is, for any DL4 code application, before building a model, we need to answer the question, how can we create training data for this problem? And the other question is, if we can create training data, how would the input code for the model be represented, right? Dr. Ramakrishna talked quite a bit about like, how do we model code, whether it is a source code or intermediate representation, and how do we, how can we implement systems which can create embeddings or encoding for the code. So those are some of the ideas which we should sort of like circle back to when we talk about code representation. So the two important questions would be, for any of the DL4 code application, would be, how do we create training data and how do we represent the input code? And keep this in mind as we go through different applications. So coming back to automatic bug detection, there are different types of bugs. Bugs which are associated with identifiers or names in the code, which is sort of like at the lexical level. We have bugs which are related with program syntax, and then there are the much harder bugs which are associated with program logic or semantics. So the particular piece of work which we are going to discuss, namely deep bugs, this is a paper from Michael Pradel and his group. This is specifically related to naming kind of bugs. So basically where the bug is associated at the surface level form of the code. So these are actually like a somewhat easier type of bugs that can be detected. And I'll walk through a couple of quick examples to show what are the naming kind of bugs. So to look at this specific example, you have a function set point, which is taking two arguments, x comma y. And if you actually look at, let's forget about what the definition is, let it be a black box. But when you look at the function called invocation of set point, you can see that like it's being called with ydim and xdim. And to a human person who looks at the code, it becomes somewhat obvious that like, I mean, it should have been, there is a bug in the code. The developer, instead of calling xdim comma ydim, he has by mistake like swapped the argument, right? So this is a kind of a naming bug where the identifiers for the arguments have been swapped by mistake. And this is a simple error which typically creeps in either because the developer did not understand the order of the argument, or it's just an oversight, right? So one more example of a name related bug, you can see the for loop that is being used here. There is an array called params, which is being walked through. So the conditional check in the for loop should actually be comparing the induction variable against the length of the loop, right? So basically like the length of the array. So you want to go through all the elements in the array. And so the conditional check for the for loop should be j less than params dot length. Unfortunately, the developer by means of, because of an oversight, has missed. So this is another kind of a naming bug where you have a wrong operand, right? For the less than operator, instead of like params.length being specified as an operand, the array params have been specified as an operand. So that is the problem here. So these are typically name related bugs. And there has been a lot of work in standard source code analysis or program analysis tools, which have tried to detect these kind of naming bugs. And those have been based on deterministic rules, right? The reason for looking at deep learning or machine learning based technique to detect naming bugs is the following, right? The rule-based or heuristic-based techniques typically do not port or transfer well across like coding repositories. The other thing is like they become extremely brittle. So if it is possible to learn a detector which can automatically detect bugs in the code using deep learning techniques, it would sort of like reduce the problem associated with building handcrafted bug detectors, right? So debugs was proposed from that perspective. And as we talked about, like, I mean, the various steps would be given a code corpus. How do we generate training data? So you have samples which are correct code and samples which are marked as buggy code. And once you have code snippets which are marked as correct code versus buggy code, you can then create a representation for these code in terms of any of the distributed representations, right? I mean, you can use code to vec, or you can use some of those other techniques. So you use a specific representation to represent these input code as vectors, and then you feed these distributed representation or vector-based representation of the code to your classifier. Like as we said, like we can have a 2-class text classifier. So you can train a classifier, and once you train a classifier, you have a model which can be used to predict like bugs in new code that is coming in, right? So this is the overall flow for building any automatic bug detector using DL technique. And we will sort of like get into how do we generate training data and so on, right? So we said like the availability of big code, where there are a lot of publicly available code repositories such as GitHub enable us to apply DL4Code techniques, right? But if you think about it, the code which is present typically in repositories is supposed to be correct code, right? So if for this 2-class classification problem, we need, let's say like the positive samples are the one where the code is, positive samples are the ones where the code is a correct code, and the negative samples are the one where the code is the buggy code. So if we want to generate negative samples, how do we really find that out, right? So one option is like to have some humans label the code in the code repositories, classifying, I mean, annotating them as correct or buggy. But that's going to take enormous effort and expense. And not only that, we may not find enough samples, enough negative samples for buggy code, right? So this paper actually like comes up with the idea of synthetically generating training data. So basically what they do is they take the code from code repositories, assume that like the code which has been present in the repositories is correct code, and then they use simple code transformation to generate artificial buggy samples, right? I mean, negative samples. So they deal with 3 types of bugs. One is argument swapping. So this was the example we saw where set point had 2 arguments, x comma y, whereas the invocation was with y comma x. And you can have like a binary operator, which instead of being used as operator A, you end up using operator B. So the example here is a for loop where you're going through length, and instead of like comparing less than or equal to, you end up using a modulus operator. And the other case for a buggy code is a wrong operand, where like you're trying to do a left shift and instead you end up shifting it with some other operand which is incorrect. So the way they generate training data is use simple code transformation. So they take an existing piece of code, identify like which of these 3 cases it can be transformed to. And they, for instance, for the wrong binary operator, they replace a current operator with a randomly selected operator. And for a wrong operand, they actually like select a random operand in the method and then replace it with that. So this is a way they are able to scale the generation of training data. And I think like that's an interesting technique to look at, given that much of the code repositories are unlabeled, right? So if you want to actually mine negative samples, it's going to take a enormous effort of annotation. and that may not scale. So this is an interesting way of like generating training data synthetically. And they go on to show actually that like, I mean, this synthetically generated training data does perform well in building a model. Okay, that is the first step. The second step is like, I mean, once I have my training data, how do I represent code so that I can build a model? So we already, Dr. Ramakrishna has covered like, I mean, how models for code can be built, such as code to vec and IR to vec. So in this specific case, they actually concatenate word embedding of the tokens to generate a code vector. So the reason why that suffices in this case is they are specifically looking only at name related bugs. So they probably don't have to consider like syntactical errors and semantical error in terms of program logic. So a simple representation where you concatenate word embedding of the tokens suffices in many cases. However, like for things like argument swapping, you also need to understand the type and formal parameter name. So for each argument, they have some additional information such as the type and the parameter name. And they also add for operands, they add what is the abstract syntax tree parent and grandparent. So basically, like, I mean, for different tasks, you would see that, like, I mean, different types of task specific representation that get used. And this is something which is somewhat different when you think about standard NLP models, right? So in standard NLP model, when we think about it, we either use word to vec, we use sentence to vec, or I mean, we sort of like look at some of the compositional representation of word or sentence embedding, right? But when you look at like DL4Code, I mean, there is additional or side effect, I mean, sorry, auxiliary information that sometimes needs to get represented based on the task. So, so that like, I mean, you get all the information that is needed, which is task specific, which enables the specific task. So this is something to keep in mind when you think about applying DL techniques to code. Okay, so I would sort of not get deep into debugs evaluation. I mean, they used 68 million lines of JavaScript code and they sort of showed that they can achieve 68% precision. But the limitation associated with this particular study or with this particular paper is that like they consider only naming bugs, and also that they are only like consider 3 types of naming bugs, right? So let's move gears a bit. Like, I mean, now that we know like we can use a DL technique like to find bugs automatically, is there a way to fix bugs automatically, right? Because that's a next step, obviously, in a software maintenance life cycle. You identify the bug, then you need to figure out what the fix is, right? So if you can get a DL model which can suggest a fix to the programmer, it actually reduces the maintenance time quite considerably, right? So if you think about it, like, I mean, this is sort of the flow that would happen if you want to build a system which can fix bugs automatically. So you start with an erroneous program. Then you have a DL model which can like sort of debugs, which identifies what are the errors or buggy statement. So now you have a list of potentially buggy statement, right? So now you need to have another model which suggests what are the fixes for these buggy statements. So you apply those fixes and then validate whether the fixes have actually fixed the program, right? So this is sort of the life, I mean, sort of the life cycle for fixing bugs automatically, right? And when you think about it, like bugs can be of different categories, right? And not all bugs are like easy to fix automatically. So for instance, if there is an underlying bug on the semantics or program logic, rather than a surface level problem, it's going to be a lot harder to fix automatically compared to something which is a surface level issue, right? So the paper we are going to talk about is a paper from AAAI 2017, which is called Deep Fix. This is from Indian Institute of Science, Bangalore. So they actually build a probabilistic program repair system using deep learning to fix common programming errors. So these are not like program logic issues, but these are typical errors which a new programmer or a programmer who is not familiar with a particular programming language may end up making, right? So you can have things like missing code block delimiter, or you can have incompatible operator or some variable declaration. At this point, you might be questioning why like we really need a separate system. After all, the compiler would report like there is a error in the code, and then the developer can go and fix it. Two parts to that. I mean, the first thing is that the compiler errors are often not intuitive. And second thing is that if a tool can automatically fix it, it cuts down, like, I mean, the development time, right? So from that perspective, a probabilistic program repair tool makes a lot of sense in software development perspective. And the way they model this problem in deepfix is that they try to model this as a encoder decoder model, right? So what they try to do is, I mean, they try to generate fixed code in the decoder, the sentence which actually fixes the problem. And the input would be actually, like, to the encoder would be the actual faulty problem. And actually, when you think about it, their DL model is very simplistic. They use a sequence to sequence model with an Bahadanu kind of attention. But the key thing to think about it is not just the DL model when it comes to software engineering task, right? The question we sort of like need to think about it is this. If let's talk about this, right? So if you think about like NLP based or human language machine translation or summarization, some minor errors, or if you're like actually like not getting the exact word or phrase which is being translated correctly, does not matter, because in many cases the consumer of the translation would be another human, and it's easy for you to infer like the surrounding meaning from the context. But think about it, who would be the consumer for the fixed program, right? The fixed program is being fed to a compiler, so it has to compile correctly and then execute correctly. So which means that if you're going to predict a fix, you have to make sure all the generated output tokens should be exactly correct. And this is a very tall order, right? Second thing is that methods can be pretty long, so you need to make sure you can handle long-term dependencies correctly. And since we need to generate correct executable code, we have to make sure we get the identifier names exactly correct. And then the problem which Dr. Dibyendu Das pointed out, how do we really verify that the generated fix is correct? Right. So these are like issues which would come up again and again when you talk about DL4Code techniques for software engineering tasks, especially when it comes to either fix generation, I mean, where you're trying to fix a buggy code, or you're trying to do automatic code generation. So keep this in mind, like as some of the challenges you need to address. Let me quickly go over the deepfix block diagram. The way they model the input program is a tuple where you have a line number and a statement. And then that is spent to a DL4Code model, which suggests an fix where like you have a line number and the modified statement. So now you might be wondering, why do we have this oracle, and why do we have this kind of a feedback loop? The issue is that a program can have multiple errors, right? So maybe like the program has more than one error. So the first time the model picks up one error, suggests like a statement wise edit to fix that error. Then you feed it to an oracle which either accepts the fix or rejects the fix, right? So if it accepts the fix, then you need to go through this process iteratively until all the errors in the code that get fixed. So this is basically an iterative repair strategy. And the oracle which is being used in deepfix paper is actually like, I mean, simple but effective. They actually use the compiler itself as an oracle. And the heuristics they use is that if you have an updated program where the fix has been applied, you check how many compiler error messages that you are getting with an unmodified code and a fixed code. So if the fixed code has fewer compiler errors, the oracle accepts the fix. If it has more compiler errors, it rejects the fix. They also have some additional heuristics or constraints where they say that the names of the identifiers and keywords in the fixed statement should match what is there in the original statement. I mean, this is to address the fact that like the code has to be exactly correct. So I won't get into the details like of the exact rules the oracle uses, but the oracle, I mean, like the idea of like using compiler itself as an oracle is like interesting and effective actually. Like, and this is something you may want to think about like when you build DL4 code applications. I mean, can the compiler be used? Can we use a post model checker, like, I mean, something like a generative adversarial network, I mean, for the Oracle or verifying the correctness, right? The deepfix was evaluated on students' written C program. So they think about the fact, like we said, two problems which need to be addressed anytime we are building a DL4Code application. One is like, how do we generate training data, right? So these people actually used student written C programs. One thing is they had some data which was actually incorrect code, but since those examples were not many, they decided to do synthetic data generation, where they take correct submission and then they seed the errors, right? So this is again thing repetitive from the debugs paper we saw. It's often the code which is present in public repositories would be unlabeled, and typically it would be correct code. So if you want to build in negative samples for your particular task, you might have to end up like generating synthetic data using programmer or compiler transformations. So they sort of show that for the raw data set, I mean, which is non-synthetic, they can fix close to 32% of the messages, and for the seeded data set, they can close up to, I mean, they can fix up to 63% of the fixed messages, right? Which is interesting. And there have been other papers which have followed up on this work. This is an interesting problem because while this paper talks about very common or surface level programming errors, there's a lot of work left to do to think about how do we infer program logic and find systems or build systems which can automatically fix logical or semantical errors. Like, I mean, so that is still an wide open topic for DL4Code. Okay, now let's move on like to another application, which is like deep code search. I mean, this is something all the developers would be familiar with. When we want to write a particular piece of code or a functionality, many of the time we look up like either GitHub gist or, I mean, Stack Overflow to find a code fragment which might satisfy our need, right? So we sort of like search for code, right? For instance, let's think about it. I want to read the data present in an XML object, right? So what would I do? I take a code search engine and I go and type the query like, I mean, how to read an XML object, right? So this natural language query should return to me a code snippet which satisfies what I am looking for, right? So again, we want to frame this into the three kind of like principles for any DL4Code application. So what is the first thing which is similar NLP problem? This is a standard information retrieval problem where we sort of like, given a query, we want to get a set of search results, right? But what is the difference? The difference is that when you think about like information retrieval problem in standard deep learning or NLP, the query and the result, both of them are in the same language space, right? I mean, it can be English, it can be Chinese, but basically like it's a human language text. So you form a query in the human language and the result is also a document which is typically a human language, right? Whereas in this case of deep code search, if you think about it, the source query domain is actually natural language because we are expressing a natural language query, but the output or the resulting domain, the domain from which the result should be returned is actually programming language or code. So this mismatch needs to be dealt with. So if you're using a standard IR based technique for deep code search, what happens is that this information mismatch or representation mismatch actually results in very poor performance. So let's look at a quick example here. So the query is how to read an object in XML. So this is a query you're going to type like into your code search engine, but the result which you actually want returned is this particular code snippet. I mean, why is this important? If you think about like surface level text similarity between the query and the code snippet, you can see that it's very, very less. So if you're using any text-based similarity approaches, they are not going to perform well. So you need something which is a lot more sophisticated to solve this problem than the standard IR text-based similarity meshes. right? So this paper, deep code search, the reference is there in the notes page of the slide. What they try to do, they sort of like try to build a unified representation for the code and the natural language query. So what they try to do, given a piece of code snippet and the associated description for that snippet, they try to project both of them into a single vector space representation, right? So think of it as like two different modes. I mean, we have all looked at multimodal representation where you have vision and text being projected into the same vector space. In this case, it's still text, but like two different domains of text. One is natural language and another is a programming language or code. And they try to force that into a single unified representation, vector representation space. And that is the key to solving this problem effectively. So let's take a quick look at this. So what they try to do is something like this. I mean, so they take from public code repositories Java methods, and that would represent the code fragment. The comment for the method would be the description or query associated with that method. So their training sample would contain 3 elements. So what are the 3 elements? One is the code snippet, then the actual description associated with that particular method, and then they also add a random wrong description. I mean, the way they try to do this is they try to do this by increasing the similarity between the code snippet and the correct description, and decreasing the cosine similarity between the code and the wrong description. So they sort of use a ranking loss where they do a pairwise similarity between the code and the correct description and the code and the wrong description. And the loss objective is actually to maximize the correct similarity and minimize the wrong similarity. Once they have built a deep learning model, which they call it as code NN, basically that stands for code and description embedding, right? So they have that model built. What they do when you're at inference time, you have a query and you have a code base. So they create these code embeddings for all the methods in the code base. And when a new query comes in, they use the description embedding model to build a embedding representation, right? And what they then try to do is they find the nearest nearest neighbors for that query, which would be code snippets in the vector space, and return that as a ranked list. So it's, I mean, if you think about it, like, I mean, this is nothing but they reduce this problem to a k nearest neighbor problem. For building the k nearest neighbors, the input representation is not like individual representations of the code and the description. They actually like fuse both of them into a common vector space and then try to find the nearest neighbors. So that is the key takeaway from this paper, because of the fact that like they are having a representation mismatch, forcing them into a single vector space allows them like to get better semantic similarity. Okay, so that is a key factor for this paper's success. I would not get into the individual block diagram due to time constraint that is present in the slide. And I mean, it's a standard NLP embedding representation. So I would sort of skip over that. Just to get back, like, I mean, the key thing to remember, like, if you want to extend this work, is that, like, I mean, you can use any type of representation for the source code and the natural language description. The key idea is to think about how they can be fused together. They used cosine similarity, but we can also think about like using other methods, like, I mean, so that is the other way of extending this particular piece of work. So the next topic or next application we sort of want to look at, which is slightly harder, is detecting code clones. So first of all, what are code clones? Code clones are one or more fragments. Like, it's very simple, right? I have a method A and I have a method B. and methods A and B do the same thing. So they are actually like code clones. So how do code clones arise? Code clones arise because people pick up stuff from public code repositories and they sort of like adapt them for their specific need. So there would be only like minor changes in the code, right? So these become code clones. Then the other reason could be some cases where there is a copy and paste or where there is plagiarism. So code clones are like, I mean, detecting code clones is very important. I mean, both from a refactoring perspective, also like from plagiarism detection perspective. So it's an important problem in software engineering. And there are different types of code clones as well. For instance, like, I mean, you could take a piece of code and just reuse it except for changing the white space or comments. There could be code clones where you have just systematically changed the identifier names and literals. So that is type 2 clones. Type 3 clones are like syntactically similar, but one or two statements have been modified. Whereas type 4 clones are the ones which are like totally syntactically and surface level dissimilar, but they tend to implement the same functionality. So if you think about it, detecting T1 and T2 is extremely easy. You can use standard text-based techniques. T3 is slightly harder. You need like, I mean, the syntactic representation as well. T4 is going to be the hardest, right? I mean, because you need to understand what is the semantics and then represent it, right? So this is exactly where DL4Code techniques perform well. I mean, the harder the problem, like it's better to use a DL4Code technique because it's going to be able to capture the features automatically, right? So we just sort of talk about like the fact that type 1 and type 2 clones, you can recover them by using string comparison or standard lexical similarity. Type 3, you probably need the input representation to be tree based. Type 4 is going to be a lot harder. So you probably need the distributed representation using embeddings and deep learning model to identify the code clones, right? So earlier work in detecting code clones was either like text-based similarity, or they had used some handcrafted features, and they don't actually work well across code bases. So the idea is like, I mean, end-to-end DL approaches can work better because they are going to learn the representation itself from the code base. So again, let's talk about this in the context of the three questions we asked, right? What is the analogous standard NLP problem? In NLP, we have paraphrase detection or duplicate text detection, right? So all the techniques and all the methods we have developed for paraphrase identification, those can be leveraged for clone detection, right? So the question boils down to how do we detect, how do we generate training data, and how do we actually like represent code, right? So for training data, like, I mean, they actually, what they do is they actually pick up code which is from public code repositories, and they actually annotate data. Like, I mean, there is actually a data set called Big Clone Bench, which has been developed for Java, and they reuse this, right? So that is how they use the training data. And with respect to code representation, they actually use RNNs like to get lexical level representation. And then they actually use recursive neural networks. I mean, like basically to capture the syntactical tree representation. So they combine like RNN, recurrent neural network, with a lexical representation, and recursive neural network for capturing the tree structure, and they combine the two of them to build a representation, which they then pass it to a standard DL model and consider it as a paraphrase, right? I mean, think about it as a standard paraphrase detect. Okay, so this paper is again interesting from the perspective that, like, I mean, you need to combine both surface level or lexical similarity and syntactic similarity to make headway into detecting clones which are not like textually similar, right? So there are other applications such as like how do we detect what are the APIs needed to solve a particular problem. I mean, this is again slightly like not so difficult. You don't have to generate the exact code snippet, but given a user query, I want to parse an XML object. The output needs to be like the APIs which can be used to satisfy this task, right? So again, you can treat this as a sequence to sequence problem using an encoder decoder and map it as a translation problem. Given a user query, which is the source translation, the target translation is a sequence of APIs which can solve that problem, right? So again, I keep emphasizing this point. Many of the software engineering tasks have an analogous or parallel standard NLP task. And once we identify what is the standard NLP task, we can reuse much of the models that have been used for the task in standard NLP. And the question to think about then would be, how do we get training data and how do we represent code? So these are the three things you need to think about when you think about a DL4Code application. Okay. And there's a whole bunch of other applications I wouldn't have time to go through, but we do have the references mentioned in the slide deck. So if you're interested, like, please do follow through on these applications. So in the interest of time, I would next jump to the concluding session of this tutorial, where we briefly touch upon the data sets, challenges, and what are the future research direction. As we said, DL4Code, the datasets typically come from GitHub or SourceForge or Bitbucket, where you have large volumes of code. But remember that these code is unlabeled, right? They are not code which are labeled for any specific task. So you are going to have lots of data which is unlabeled. So one way to start with building models is use language models, so that you don't need labeled data, or think about using unsupervised or semi-supervised approaches. But the fact that we have large amount of unlabeled data also means that we don't have task-specific benchmarks for many of the software engineering tasks. So if you look at specific task-specific data sets for DL4Code, they are very small data sets. I mean, you have this big clone bench that is typically used for code clone detection. Professor Ramakrishna mentioned a few data sets in the context of program representation. For defects, there is a defects4j Java-based data set, and there's also another data set called BugSwarm. So this area needs not just newer techniques, newer models. We need more label data set which are task specific. I mean, for instance, when you think about standard NLP, we have glue and super glue and so on, which are like standard NLP tasks benchmarking, right? So we really need a DL4Code benchmark for different software engineering tasks, and that is something to look at from the research community into developing it. So the challenges, again, Dr. Ramakrishna and Dr. Dibyendu Das mentioned some of this. Collecting label data for each task would require massive amount of annotation. And you also need domain level expertise. I mean, for instance, how do I really know this code is buggy, right? I mean, so you need considerable expertise to annotate. We also need proper benchmarks and the evaluation metrics. The most important problem is that how do you verify the correctness, right? I mean, when you do probabilistic program repair, right? How do we really ensure that the code that gets generated is correct? And this is a problem Dr. Dibyendu Das touched upon at the end of compilers. I mean, can we build a post-pass correction tool, right? So this is a problem which is wide open still at this point, and that is probably one of the reason why DL4Code has sort of yet to take off on a big time. I mean, it's possible to use DL4Code techniques for augmentation, right? I mean, in terms of assisting the developer, if you want to tell him this is the coding convention, this is the comment generation, and so on, those kind of assistive tasks, DL4Code I mean is obviously best fit at this point. But when you think about using DL4Code for automatic code generation, we run into this problem. How do we ensure the generated code is correct, right? So that problem still remains wide open. I mean, there's been a lot of, I mean, I guess most of you would have seen the hype that was in the news, I mean, when GPT 3 was used to generate, I believe, JavaScript code and Python code from natural language description. But that problem remains is that, like, I mean, how do you really ensure, I mean, when a programmer specifies an intent, the code that gets generated by some of these DL4Code model actually like is correct, executable, and satisfies the logic which the programmer has intended. So that problem is still open, and that's one of the major challenges like going forward in doing this. So the areas where like research needs to happen, how do we ensure correctness? How do we build real world applications, data sets, and benchmarks? The most important thing I think somebody talked about, like in the question answering, can we use either transfer learning, multitask learning, or use of pre-trained models? So these are some of the areas to think about going forward. But as I said, this topic is like just taking off. So there's like a lot of scope. I mean, that's a good news and the bad news, right? So there's like a lot of scope for new research, but at the same time, like there's a lot of pitfalls. I mean, because you don't have standard data sets, you need to create your own data sets. You need to find mechanisms to ensure correctness. So that's a good and the bad news, I think. Like, so to conclude, like, I mean, there's a bunch of references. I mean, there's an excellent survey on source code modeling, which is the first reference mentioned in this slide deck. So that would be very useful if you're just getting started on this area. There is a survey, the reference 3, which talks about how big code and naturalness can use are relevant factors for machine learning techniques. So basically, the idea is if you're starting off in this space, go through some of these specific references and then pick up a specific software engineering task where you think like the newer DL techniques would be relevant, and then try applying them. So I would stop here, like, and take questions, like if there are any. So I do see that there is one question in the chat window. In addition to, I mean, let me repeat the question for benefit of everybody. So the question from Mr. Soham Ghosh is this: in addition to the code and its description, does it make sense to use the indentation as well for training the classifier? Very good question. In fact, like, I mean, there are a couple of papers which actually use the indentation as one of the metrics, like in building the representation. So yes, it makes sense, like, I mean, to use it. I mean, again, this would be task specific, right? So if you're, I mean, for instance, if you're doing code convention or, I mean, some of those similarity measures, yes, or clone detection even. But when it comes to like creating probably the API sequence, or I mean code summarization, probably the indentation might or might not be that helpful. So it's a task specific requirement, like on what are the information that would be useful in addition to the actual code itself. Like, I mean, so very well, I mean, like a very interesting and important question. So this is something like, I mean, we are trying to learn as we go forward and build DL4Code application, what auxiliary information in addition to the code would make better models. So with that, I would stop and thank the organizers for giving us time to present this tutorial. Again, I would encourage like the listeners like to get involved, because this is an area that's developing, and we really need a DL4Code community to build and start answering some of the open challenges in this space. Thank you.
So thanks, Sandhya, thanks, Divyendu, and thanks, Ramakrishna, for such a wonderful tutorial and eye-opening talk on DL4Code. And we really got very insightful knowledge about how deep learning can be used on programming languages and to solve many interesting problems. So I thank everyone. Thanks to the audience. And I think it's time to conclude this tutorial. So thanks, everyone.
Thank you, folks.
Thank you, folks. Have a good day. Bye.
Okay,
bye.
Thank you, everyone. Thank you very much. Take care. Bye-bye.